Hello, everyone. Doesn't look like anyone's here yet. Hello. So this is a little bit earlier than normal. Hopefully that'll be okay. Today's topic is going to be quad trees and destructible terrain. So let me open up MS Paint, our lovely friend MS Paint, and give you a little bit of a demonstration of what is a quad tree, because I'm sure some people are kind of wondering what that is. Make this a little bigger. So let's say I have a map, a section of the screen or something. Now, I want to kind of track stuff on this, right? Similar to what we did yesterday, or not yesterday, last week with the wave function collapse. We sometimes have little pieces that are different from others. Let's say that each one of these is a single pixel, and we need to be tracking all those pixels. Well, that's not too bad for a square this size. That is, what is that? That goes from 100 to 600, 200 to 700. So it's 500 by 600 pixels. That's not a lot of elements to have to keep in a list. So if we needed to, we could actually keep, let's say I wanted to actually deal with some maybe terrain in here. So let me actually fill this. That's not what I want. Fill, solid color, I think. There we go. So let's say I've got some terrain here, like that. And I want to track which elements have terrain and which don't. Now, there's a couple ways I could go about that. One of them is I could treat this as, oh, there's always terrain above X. Or you could do like you see in a lot of platformers like Mario, where they say we've got specific blocks that have been built up. And the more important thing about a lot of that terrain is a lot of that is not actually tracked on the individual pixel level, right? It's larger chunks, maybe 64 by 64 pixels, which makes it a lot easier to track because your map essentially at that point becomes a lot smaller to have to keep in memory. But if I want to track this on the individual pixel level, that's actually going to be kind of a lot of pixels at some point. So right now we've got this 500 by 600, which is a lot, but not terrible. And so I could keep each individual little pixel value. So here there'd be a whole row of pixels. Let me actually make my cursor a little bigger too. I could have a whole row of pixels that is just all zeros because that indicates, that they're all this empty color, the sky. Another row, another row, another row, all the way down, and then I get to here, and then all of a sudden I start having entries in the array that aren't zero, that are a non-zero value, because that particularly was, because that's, like, why is my text not showing up? My text is not showing up because it's white, and this is a white background. Okay, we'll fix that at some point. At that point, you come to this row, and all of a sudden you're trying to track values that aren't zero. That works. That would actually work perfectly fine, except there's a lot of this that is just contiguous space. And by contiguous space, I mean it doesn't stop being empty. So there's probably more than half the rows that I would have to be doing if I was doing a two-dimensional array would be just completely empty space. That's not very helpful at all. So what if I divided this into quarters? So let's divide it. This is not going to be very good quartering. Let's say I divide that into quarters. Okay. So now this entire space, I can basically say, oh, I know this is all empty. So I'm going to store one number for it, one single number, and that's just going to be white, empty, or sky, whatever. This one, same thing. This one, same thing. This particular one now has to be a little more complicated because it's not entirely all one contiguous color. Some of it is terrain. So this one I can break up and say, okay, here, let's do this array, let's do this array, let's do this array, let's do this array. You see how much storage we've saved there? Because now instead of having all these thousands of tiny little images or tiny little array elements that are all going to be holding the same thing, I just know I've divided my screen into 4. And these 3 are represented by a single number, which means I've reduced the amount of space that I have to store by 75%. If this was, let's say this is 500 by 600, how much is that? Let's just see exactly how many pixels that is. 500 times 600. 300,000 pixels. So let's take 25% of that. That's not what that was supposed to do. Math. We're supposed to multiply. There we go. To get percentage, and actually, there we go. So we've gone from 300,000 array elements to 75,000. This matters because every time we draw to the screen, if we're doing on a per pixel basis, we have to draw every single one of these, which means we have to loop over every single one of these entries. So cutting that down is really helpful. What if we divided this into quarters again? So these three we don't really need to quarter because there's no need. They're already represented by a single data value, and it's just 1. So if we quarter this again, here and here, well, we discovered something interesting now. This lower section here, this is also represented now by a single element, or a single value. So these are zeros, this is a 1. So now we've only got to worry about these 3. All right, so these particular 3 squares, because they're the only ones that can't be represented by a single value. What if we do it again? Okay, so for all these ones that can't be represented by a single value, we're just going to draw those lines through them again, order them again. Well, now we've got 2 more sections that also, well, actually a bunch. Look at, we've got these 4 sections here on the left. These are all represented now by a single value, and these 2 are represented by a single value. So now we've just got this tiny little chunk of space here that we need to think about, and we need to worry about representing the individual values of them because all the rest of these are all single values. So we've cut down the amount of storage that we need to have, even for this 500 by 600 pixel block, to just these little chunks. Which, if this is 500 by 600 pixels, this would be a quartered again and quartered again. Well, let's see. Where's my calculator? Did I lose my calculator? Let's figure out exactly how much that is. So we started off with 300,000. Okay, let's quarter that. So each one of these represents 75 pixels. If we quarter it again, each one of these, this represents 18,000 pixels. If we quarter it again, each one of these represents roughly 4,000 pixels. So we've got 1, 2, 3, 4, 5, 6 of these blocks. Oops. That's not what I want. So 4,600. Let's just pull that back in. 4,600 times 6. We're now only looking at 27,000 elements in an array, whereas before we were looking at 30,000 or 300,000. So by doing this quartering system, we've managed to get down to the point where we're only looking at 27,000 elements, and we're looking at less than a tenth of the original numbers that we had to deal with. Why does this matter? Well, because if you actually are building something that is like a video game type thing, and you're building terrain, you may want that to re-render 60 times a second. And I can tell you, you can get a lot closer to that 60 times a second if you're only having to render 27,000 locations as opposed to 300,000. JavaScript is actually pretty fast at going through 27,000 locations, even if it's a bunch of tiny little things that have to be done. But we can go even further in this. So let's zoom in a little bit on this particular block here, and just assume we're doing this for all of them. Okay, what if we just quartered this one as well? Well, now we've got 2 blocks here. These are represented by a single value, so they get completely eliminated. These 2 can't be because they've got this tiny little bars there. But if we quarter them again, now we've got these even smaller spaces that's just got that single little line there. Now, in reality, these thick blue, black lines wouldn't be there, so it wouldn't be completely that single pixel, but you can see the point. If we get down here and we quarter this even smaller, now we're getting an even smaller amount of area. So imagine just that thin little line along the top. That's the only thing we need to store because everything else is being tracked in this structure. So if we zoom out a little bit more, you can see how far down that goes, and we can keep going further. down to the individual pixel level. Why does this help us? How does this help us? Well, because one, you can see we don't need to go down to the individual pixel level on this block here. Why would we need to? It's going to be the same value as everywhere else. Same with this block here. We didn't need to jump any further down into it because it's already all green. We can just assume it's all green and everything inside that is green, and we don't need to really deal with narrowing down any further into that. The other reason is because this is a tree structure. It's not a binary tree, which, we're used to working with. It's a quad tree, and that's why they call it a quad tree. It's each node has 4 children at most, but the children are only opened up if there is something inside that node that can't be represented as a single rectangle. So for example, in this top left node here, it has no children because it has no need to have children. If I suddenly put a square of green inside here, like this square, all of a sudden this would need to have children to represent that. And so we'd actually have to go in and start drawing those lines and saying, okay, now, oops, I'm still in the box. Now we need to start quartering this to get down to that point so we can figure out exactly which sections of the child handle all that. And we do the same thing as we did here. We go super deep into that all the way down to get that. But until we add pixels there that are different from the rest of the screen or the rest of that section, we don't need to do that, which means that we can save on that storage space. Of course, this means that if I just was to draw a green line all over this or use like the spray can tool, then this all becomes kind of inefficient. However, it's never going to be as inefficient as storing all these pixels individually. Because the most inefficiency you can have from storing all the pixels individually is width times height. The most inefficiency we will ever have from this is if every other pixel is a different color and there's no contiguous blocks at all, which, let me zoom in really far and I'll show you kind of what that would look like. So what that would look like is if I had something like this. And I don't know if you can see that really well, but in this case, there's actually, in this checkerboard, kind of a checkerboard-like pattern, there's actually no way to store these in any sort of contiguous blocks. I can't zoom in any further, sorry. But in this case, we are just as bad as the width by height, because then we have a cell for every single one. We've got a little bit of extra overhead because of the tree structure. So maybe it's a little worse, but this is an extremely uncommon pattern to have across your entire map. Even though I had it just across this little section, for this tiny piece, it would be just as efficient. But for the rest of the whole structure, it would be more efficient. So that's why a quad tree is going to be more efficient for storing data of this sort. Now, again, if you can make your data something that that isn't on a per pixel basis, that's a little bit larger, like 64 by 64, you don't need something like this because you've got few enough objects in your system anyway that you'll be fine. But for something this size, if you're going onto that per pixel depth, you need something a little bit better to hold that. What this is commonly used for, and again, just like last week, this is something I found on YouTube and thought was really cool. What this is used for is, the example I saw was destructible terrain, like for example in World of Tanks, where you have, excuse me, you have those two tanks on either side and they're firing bombs and missiles at each other, and as those bombs and missiles hit, they destroy the terrain. Well, if you were using 64 by 64 bit chunks for that, and you tried to destroy your terrain that way, you would have to take 64 by 64 bit chunks out of the environment. But if you want your terrain to be fully destructible down to the pixel level, you need something that can handle removing it at the pixel level, and that's what a quad tree is good for. Are there any questions about this concept so far? And if you chat now, it should actually show up on the stream, hopefully, because I tried to get that set up. Anyway, today we're going to try to build something like this. All right, no questions so far. If you have questions, please shout them out. So we're going to try to build a quad tree system that lets you enable, disable terrain, stuff like that. So the first thing we're going to need, let me open up my, that's not it. Let's go to our code area that we're putting all this code in, because I know some of you might want this in the end. All right, so let's make a new folder here, and we'll call this folder. What are you doing, VS Code? There we go. Quad tree terrain. All right, and then I'm just gonna go ahead and open up just that folder. Quad tree terrain. And then what I'm going to do is I'm actually going to start. Now I'm trying to get my terminal to function appropriately. Terminal, behave. I'm going to start a terminal up and get a sample React app because, you know, we like working in React. React is good to us. So let's go. Video. We're going to go into the quad tree app. We're creating an app. We're going to put it in this directory. Quad tree terrain. This is, let's use Vite because Vite's kind of faster. I'm not going to use that to start off with. And let's see, let's go and let's install our modules. And then we'll just let that run for a little bit. Let me zoom in a little bit here so that you can see what I'm doing. View, appearance, zoom in. Okay, so to start out, what we're going to need to do is we need to have a binary tree. And binary trees, there may actually be a JavaScript implementation of a binary tree at this point, but we're just going to make one because they're not the hardest thing ever. So inside here, I'm going to put a utils directory. And what utils stands for is utilities, because the binary tree is a generic object or a generic concept that we may use in multiple places. So I'm just going to put in here and I'm going to say binary tree. Okay. And then let's make a class, binary tree. So a binary tree is going to have a root node, right? All trees have to start with a root. So we're going to keep a close eye on that. Let's put our constructor and this dot root. And we're just going to set it as null to start off. So we've got our binary tree, we've got a constructor, we've got a root. The next thing we want to be able to do is we want to be able to add things to a binary tree. Now, this particular binary tree, we want to be able to add children to it, but we kind of want to be able to add children to it in a special way. We need to be able to add children at certain coordinate points, right? So if we go back to our list here, if I suddenly, oops, I'm in text, that's why. If I suddenly go ahead and create this green square here, I am not going to just be wanting to add a random number to a binary tree, which is maybe what we've done before. I want to be able to add elements to a binary tree at a very, very specific location, right? But for now, I'm just going to make kind of an add function to it. And let's just say x, y, and value, okay? We're not going to do anything with that right now. I just want to have it there to start off with. We're also going to want to be able to remove an element at x and y. So remove x and y. So this binary trees can be a little unusual than other trees because it's kind of a coordinate-based tree. Where your element is on the tree structure has to do with what coordinate you're at. All right, so let's take a look then. We're going to need a node. This is because if you do a linked list, if you do a tree, anything, you need some object that is going to be your root. It's going to contain all these properties. Now, these properties, well, let's take a look at this for a minute. What if I've got this larger outer cell of my map, and then I've got these inner cells? What are some properties about them? Well, they all have a specific value, right? So we need to be able to have a value on these nodes. So let's add that in. Class binary tree node. Okay. And we're going to have a constructor. We're going to take a value in, and we're going to save that value. That's a singular value. Now remember, the reason we can do a singular value there is because every single one of these nodes is supposed to be broken down to the point where there's a single value inside of it. Like you can see here, these nodes here have a single value, these ones have a single value, etc. This one doesn't exactly because I did that little thing in the corner. These ones kind of don't as well because I don't want to go that deep into the example. But in our actual code, each one of these is only going to have one value because that's kind of the whole point of the quad tree. It's also going to have children. Every single node in a tree, and actually, you know what? I realized I called this a freaking binary tree. I'm just going to call this a tree because it's not a binary tree. It can't be a binary tree because a binary tree only has 2 children. And this is going to have 4 children. So I could call it a quad tree, I guess, but I'm not going to. Every node is going to have children. That's what allows it that recursion down into the system. So we're going to go and we're going to add this.children, and we're going to set it to an empty array. The other thing that's important for us to know about these individual nodes is they have an x, y, and a width and a height. Every single one of them does. They have the x, they have the y, they have the width, they have the height. That's just how they work. Every single one of them is position based, right? Because these trees, if we do it as a tree structure, it's that branching down structure, but they also need to represent a certain section of visual space. So for example, this particular, well, the root here goes from 222,131 all the way to 709,615. So those are the coordinates that it is responsible for. Any of its children need to fall within those coordinate pairs. This one, well, let's take this little one, for example, 530 to, or 527 to 379, and then it goes to 584 and 440. This is a smaller group, but it's the same idea. It's responsible for this little chunk. The beauty of a tree structure like this is children don't need to even know they have a parent. I've got this child here. As far as it's concerned, it doesn't have any children, and this is the only chunk of space that exists. It's just this little bit in here. This one happens to know it has some children, but it doesn't know about this square over here. It doesn't really have to because that's somewhere else. So we've got 4 children, but we also need a coordinate pair. So there's 2 ways that we can do that. We can represent any rectangle with 2 x and y coordinates, or an x, y, and a width height. Either one of them, they're interchangeable with each other. You can get a width height from 2 x and y coordinate pairs. You can get 2 x and y coordinate pairs from a width height. I think I might go with a width and height just because that's easier to understand cognitively. So as well, we need here x, y, width, height. And then we're just going to store that. Y equals y. This dot width equals width. This dot height equals height. Cool. Now we have a node that it stores a value. It knows if it has any children. And technically, if it has children, then the value doesn't matter because we know the children are going to be what has the value. If, by definition, if this tree node has any children at all, it is not a contiguous value, which means this property can pretty much be ignored. We have our x, we have our y, we have our width, we have our height. So now we have the space that node takes up. Now we need to get into, okay, how do I add an x and y? If I want to add a single pixel into this tree, how do I do that? Well, that's where things get really complicated. So first of all, if we don't have, well, let's do this. We started off our root as null, but really we probably should actually start it off with an x, y, width, and height. Because when we start off our tree, we know the area that it covers, and we kind of want to have a node to handle that. We want something tracking that space immediately. So I'm going to change this constructor so it actually takes in x, y, width, and height. And then we're going to set our node to a new tree node. With, I'm just going to do the value of null, x, y, width, height. So now we've got that. Now when we add something, if we're going to add something, we basically need to go into our root node and say, hey, listen, I need you to set this pixel. Either it's going to be you or it's going to be one of your children. So what I'm actually going to do is I'm not going to do that necessarily. Well, no, I could do the recursion here. I suppose we could do that. So if we've got a tree structure, and let me pull this out a little bit more so that I can actually draw some stuff here. We've got our tree structure, and this is going to be, it's going to have 4 children. Okay. And so let's put all of our child nodes here. Here's our root. We've got 4 children because it's a quad tree. These children will each have their own 4 children. I am not good at drawing trees. There's probably some way that I could have something generate a tree for me. Maybe I'll look into that. These have their own, and each one of these is a quarter the size of its parent because of the way the quad tree works. Here's the root. We've gone down here. We're now in this little chunk. We go down here. We're now in one of these chunks, right? Maybe we go down this path here. And we're in another smaller section. We're in one of these little guys. And so that's the whole point of a tree, is we need to be able to traverse down that tree, but we also need to be able to generate those children as we go along. Because as soon as, if we start out, let's do a slightly smaller example here. We start out here, we've just got a root node. As soon as I add a single pixel in here, that is entirely too small, so I'm going to add a small rectangle in there. As soon as I add anything in here, I immediately have to bisect all the way down into that because I can only store one value. Which means that when we get to our add code here, for that single x and y, I need to be able to recurse down into my tree to find that position, but I also need to create and generate that tree as it's happening. So to look back here, let's say I needed to go down this branch all the way down to here. I'm just realizing the chat is covering part of that. So that's important for me to be aware of. Let's just move all this over a little bit. There we go. And now this is white, which I don't want it to be. There we go. If I need to go down, and now I've cut off part of my other quad tree. Oh well. If I need to go down this branch here and go further off, I need to generate all 4 of its children. And then generate all 4 of the children on every, until I get down to the right depth, because you notice as soon as we go into this, we need to have all those children just so we know which ones are empty and which ones aren't. We need these, in fact, would need to go all the way down to the pixel level. These particular squares, but each time they're leaving behind some of that isn't there. So there has to, it's not like in a normal binary tree, we have up to 2 children. In a quad tree for terrain, like we're doing here, we either have 0 children or we have 4. There is no in between. We can't have just one child. That's just because that's the nature of how it's set up. Though I guess we could technically have just one child, because if I'm drawing my box here and I just have this one child, then I don't need to know about these because I can kind of assume they're the same as my parent value. The thing is that gets complicated because then I have to figure out which child have I not added. So then our algorithm becomes more annoying. If I need to add suddenly this child, I need to think, oh, did I already add that child? How do I go down that? And our algorithm for recursing becomes more complex. If we're always generating 4 children, we can always generate them in the same order. So then we can always know which one of them is where. So for example, if I generate them in 1, 2, 3, 4, then I always know which one is my top left because it's always going to be the first one in my children array. I always know that the bottom left is going to be the third element, the bottom right is going to be the fourth element, and that helps me when I'm recursing because it makes the code simpler. This is a case where we are going to be taking up a little bit more storage space in some cases because we do need to generate the nodes here, but it's going to make our algorithm more efficient, and that is not a bad thing, going over all of this, because we're going to have to do it so many times. So when I add, I need to start from the root node, and I need to recurse downwards into the tree until I find the point where I have a width and height of 1, and the x and y coordinates match, and then I set that value. But all the children up to that point need to exist as well because of that tree, that way we're doing that tree. So we're going to start off with a current node, and we're going to set that to this.root. And as I add, first I'm going to say, okay, x and y, we have our x and y. What quadrant does that fall into? Where is that? And that's when we have our x, y, width, and height. So we've got 4 quadrants. The first quadrant, we know we're going to fall to the left of that. Well, actually, let me just visualize this for you all. If we've got our quadrants here, and let me put some text on these just so it's clear. Quadrant 1, 2, 3, 4. If this is a normal graph line, to the left here is negative y, to the right here is positive y, positive x, negative x. We can actually look if this is our x and this is our x plus width, and this is our y and this is our y plus width. Let me actually just draw that out so that we have that info. And let's put that in here, and then I want to drag this down a little bit. Let's put some text on this. This is going to be y. This is going to be x plus width. This is going to be y plus height. And this is going to be x over here. Let's move that a little closer. This is where you start getting into actual geometry. And for those of you that are saying, like, I don't understand math too well, that's okay. I'm going to explain this stuff to you. And this is off the screen again. There we go. I'll explain this to you. If you're doing game programming, this is why math becomes important. Because you are going to be using a lot of geometry, a lot of trig. So in this case, if we're trying to find if something is in our first quadrant, why are we trying to find that? Because if it's in our first quadrant, we know that is going to be our first child in our children list. We can recurse into our first child. To find that out, we need to actually, this line actually represents x plus width divided by 2. So this particular, let me see if I can get here. X plus width divided by 2 is this line. So this is x plus width divided by 2, which means if the x coordinate that I'm getting here is less than x plus width divided by 2, it's got to be on this side, which means it's either child 1 or child 3. Then that's where the y line comes in. This line here is actually y plus height divided by 2. We'll draw another little line there so that's clear. Which means that if my y coordinate that I'm getting for the pixel I'm trying to set is less than y plus height divided by 2, then it's going to be 1 or 2. So I can use those two checks to verify which quadrant of my space that I'm in. You know, I wonder what if y plus height is odd? We could just decide to round it. It doesn't actually matter at that point because as long as it's consistent, as long as we know something is going to be on either side and we don't miss a pixel, then we're okay. So this is kind of complicated, right? This is a bunch of complicated math. I'm just going to put it all out here. We're going to say below halfway horizontal. So what that's saying is it below my halfway horizontal line? Which means it would be here. Or is it above? So that's a simple true false that basically says, does my pixel fall in this section or this section? Is it a 1, 2 or a 3, 4? How I'm going to do that is I'm just going to check if the y that I got is less than this formula. Or is it greater? We know by the simple fact of our recursion that y is never going to be outside of these two lines. So we don't really need to worry about that boundary check. So this is going to equal y, which is, here's our current coordinate y, less than, okay, then I'm just going to say current.y, y plus current.height divided by 2. This is that same equation as here. Y plus height divided by 2 is our y less than it or greater than it. Being able to take a math equation like this and translate it into code is an important skill. So now we've got our y less than our current y, our border plus half the height. So is it in these two top or is it in these bottom two? We're going to do the same thing for the vertical. And I'm realizing below halfway horizontal, below, yeah. So this is actually kind of confusing. So I'm just going to say below halfway y and below halfway x, because vertical and horizontal, technically y is supposed to be the vertical and x is supposed to be the horizontal. So I don't want to confuse that. But this is basically the exact same thing, except I'm replacing the y's with the x and the height with the width. So now, based on these two booleans, I have 4 choices. True, true, which means they're in the bottom, or they're in the top corner, top left. Sorry, I realized my camera's backwards, so this is looking like top right to you. My top left. Then, if one is true but the other is true, it means they're on one of the diagonals. If they're both false, it means that they're in this other section, the bottom right. So this is true, true. This is going to be, these two are going to be if one of them is true and one of them is false. This is going to be if they're both false. That means that we now have, this runs extremely quickly. So this is an extremely quick way for us to know which child we want to work with. So I'm actually going to do and say, okay, const child index equals null. Well, let's just do -1. I want something that if this check fails, it's very clear there's a problem. So -1 is never an element I'm ever going to get in my children array. So this is perfectly fine for this. If below halfway x and below halfway y, that is going to be this particular one, which is child 1, which is the 0th index of our children array. So I'm going to say child index equals 0. And this actually needs to be a let. Else, if below halfway x and not below halfway y, well, what's that mean? Below halfway x, so it's on this side. It's below our x halfway. It's not below the y halfway line, which means it's on this side. So it's 3. This is element 3, which, because we're 0 indexed, is going to be 2 in our child array. Child index equals 2. I'm just going to copy this. If not below halfway x and below halfway y. So what we've discovered there, we are not below our halfway x, so we're on this side of the system grid. We are below our y halfway, so we're here. So we are 2, which 0 index turns into 1. So we're going to say our child index is 1. The final one, and I'm just going to put it in here specifically, if we are neither below halfway x or below halfway y, both of these are false. We are here by definition because we have to be on this side, but we also have to be on this side, so we're in child 4, which 0 indexed is the 3rd child. Any questions on that? I know that was a lot of math I just threw at you. Let me know if any part of that is confusing. Just a little bit of time. I should have a little timer that like counts down and plays Jeopardy. All right. So now at this point, we know, based on our coordinates, which child we need to recurse into. What do we do if we don't have any children, though? So we could be at the point where we need to recurse. We're at this current node, and we need to recurse into child 2, but we don't have children. So we need to create the children now. So we're going to say if current.children.link equals 0. So if we have no children, we need to generate them, all 4. The reason we want to generate all 4 is because if we don't have 4 children, this indexing doesn't work the right way. We can't assume the index of where each of these children is unless we're generating them all at the same time. If we're generating them all ad hoc, then they could be anywhere in our child list, which means we actually have to do a search into the child to figure out what index it actually is, which is going to be more expensive. It's not too expensive. It's not like super expensive, but it is an extra step that we need to take. And it's just extra work that we don't need to do. And this is much cheaper. So first child, 1. This child has the same X and Y as its parent, but its width and height are cut in half because it represents this particular quarter of space. So we're going to say current.children.push new tree node. We're going to start off actually by giving it the same value as its parent. Why are we doing the same value as its parent? Because when we initially subdivide here, we have no reason to believe it's not the same value as its parent. If we set a single pixel down here, 90%, 99% of the tree nodes we generate are going to have the same value as their parent. They're just going to go in until you get that one single pixel that doesn't have the same value as its parent. Right? So we can assume right off the bat that we're the same value as the parent, and that should be okay. The next thing we need, I believe, is the X and Y. That's going to be the same as our parent X and Y because we're looking at these borders here. The only change now is our width and height. So the width is going to be half the width of its parent because we're subdividing into quarters. So that's going to be current.width divided by 2. Okay. The height, same thing. Current.height divided by 2. And let me actually put these on separate lines so it's a little less confusing. So that's our first child. Top left child, which is at index 0. Our second child, our child index 1, is not below the halfway of X, but it is below the halfway of Y. So we're looking at this child here. Its Y is actually going to be the same as its parent. So let's just pull that in real quick. Let's say, okay, this is going to be a top right child. Its Y is going to be the same as its parent. Its X is going to be something different. The width and height are also going to be half that of the parent. What is the X going to be? The X is going to be this line, which is X plus width divided by 2. So this is going to be current.x plus current.width divided by 2. That's where it starts. Next one, child 2. It is below the halfway X, not below the halfway Y. This is our third child. This one, the X is going to be the same, but not the Y. Okay, so we're going to go in here. We'll copy this again. This is the bottom left child. Bottom left child. The X is going to be the same. The width and height are still going to be half. Like this. They're still going to be half of the parent. That's a constant. The Y is going to be this Y, which is, or 3. No, the y is going to be this y, the height. No, that's not right. No, this is the y, right? Because this is the y here. I actually did these. Yeah. So these are both pointed to the same thing. That's why I was confused by that. Oh my God. I was looking at this. I'm like, wait a minute. Why? That doesn't seem right. But that's why, because this is supposed to point to that line. So this line is y plus height divided by 2. And that's going to be our new starting y of our individual grid. So this is going to be plus current.height divided by 2. Now we have our final one, our bottom right child. This one, the x and y are both changed from where it is. So this one, put that in there. Bottom right child. This, the x is going to be current.width divided by 2. The y is going to be current.height divided by 2. And these two are going to have the same width and height. Now we have our children. We have all of our children put in there. So we've generated all 4 of them. We now have these things. Our tree now looks like this. So we can now recurse into the child. So we're going to do that by basically doing an infinite loop. Recursion and infinite loops get along. This is technically not like... So if you've heard of dynamic programming, this is actually dynamic programming. Recursion would be if I called another function and said, here's the next child to work with. Please recurse into this function with that child. Dynamic programming is where you turn that into a loop that runs a certain number of times. I'm using dynamic programming here because recursion can occasionally run off the end of the stack if you go too many functions deep. And because we may be going kind of deep, I don't really want to do that. So after we generate our children, this loop is just going to run forever right now. That's pretty much what it's going to do. Forever, forever, forever. We don't know we really want that. We have to change our current pointer to do that. So at the very end here of this, this whole if block, let me just collapse it. Create children necessary. We know our child index. Current is now going to be current.children child index. We're going to recurse into that current. But this is also never going to end. Because what's going to happen is we're going to just continuously loop forever, going deeper and deeper and deeper towards this x and this y. So what do we want here? If x equals current.x and y equals current.y and current.width equals 1 and current.height equals 1, at this point, we are at the single pixel level and we have found the right pixel. We can now change that color. Current.value equals value and break out of the loop. We get here, we found our pixel. Set it and quit. This is our end case. If we don't have this end case, it's important that every recursion, and even though this isn't technically recursion, it kind of uses the same principles, it's important that every recursion have an end case. The case at which it finishes and says, I'm done doing what I needed to do. This is that case. We found a single pixel, a node that is 1 pixel large, 1 by 1. And it matches the coordinates that we gave. Well, then we're going to set the value. At this point, we've created children for every single level on that tree. So we've built that whole graph state down as far as we need to. Let's test this. It's definitely important to write some tests. So I'm going to make a tree.test.js function. .test is a common convention that we use when we need to put something in that is the test file. You notice it has the same name as the file that is being tested. It just has test. What I could do is I could actually pull in a Jest framework or Mocha or any of the other test frameworks and write some actual unit tests for this. Even though this is technically a front-end program in React, it's not out of the question that I actually could have some unit tests, especially for something like this. Nothing about my tree and tree node here is front-end specific. Nothing at all. These are all going to be something that can be done on the back end or front end, which means I can use a back end test framework for it easily. I'm not actually going to do that though. I'm just going to write a couple of standard little mock test code just to make sure this is doing what I expect it to do, because I don't really have the time to write a ton of unit tests right now. If this was the only thing I was doing today and I was just doing this tree, I would write unit tests galore. But yeah, I don't really have the time. So let's import. Oh, you know what? Actually, let's export our tree first of all. Now here's where you get to kind of a problem, because if I export this and I say like export default tree, then when I import this, I have to import tree from tree.js. And if I run this now, let's just take a look. Let's say node, let's make this a little bigger as well. Node source utils tree.test. It's going to say, hey, what? I can't do this. I can't do an import statement. So we need to do that. That's kind of the problem, because if I actually want this to be a front end thing, this is how front end does its exports. And if I want to import like this, then I have to figure this out. So let's actually take a look here, see if we can figure out how to make Node do this, because I've not actually done this before. Let's say Node use required JS syntax. So I think that's what this is. Oh no, this is common JS, sorry. Common JS modules. Let's see. Common JS modules are the only way to package JavaScript code, blah, blah, blah. It supports this standard used by browsers and other JavaScript runtimes. ECMAScript. ECMAScript here, this specifically is, I believe, let's see, ECMAScript modules. Yeah, this is the ECMAScript. So we need, this is the import and export that we need Node to understand. So I need Node to enable this. ECMAScript. MJS file extension. Okay. For the package.js type field or the input type field. Outside those cases, Node will use the common JS module loader. So what I can do is if I come in here and I change this to MJS, it sounds like Node might treat this like it's a, and let this import work. So let's try that. MJS. Unexpected token export. Oh, because this also needs to be MJS. Because it needs to know it's a module. Well, that's fun. Well, let's just try it. Let's just get it to work. Okay, that worked. That did something. So now it didn't complain at least. What if I make a new tree? New tree. And I just console log my tree. Let's see what happens there. Be something interesting anyway. Okay, it gives us a tree, and it says, hey, you've got a root, value, children, x, y, with height. Beautiful. Beautiful, beautiful. So let's create an actual tree with some actual real parameters. Let's give it our x of 0, y of 0, and a height of 10, right? Let's try that. Okay, 0, 0, 10, 10. So now we have a 10 pixel screen. Let's add a coordinate to it. Tree.add, let's say 4, 7, and then let's put a value of 1. And then let's console log our tree again. This is the part where everything's going to break. It's looping forever. We've got an infinite loop. That's exciting. Let's check that out. And I know an infinite loop because it should not have taken longer than a millisecond. Okay, so let's just go in here. While we're in our y true, let's take a look at what element we're looking at. Current.x, current.y, current.width, current.height. And I need to hit Control-C real quick here, otherwise we're going to lose our output that we want. Ah, close. Okay, so we start off with 10, 10. That's fine. We start off with 0, 5, 5, 5. That's also okay, because we gave it 4, 7. So it tried to go into that coordinate, which makes sense because that is 0 and 5. I think is going to be that that kind of third child there. Then it goes, this is where we start running into problems. It goes to 2.5. And you notice now the numbers just start getting smaller on this side. That's a bit of an issue. And finally we're like, oh yeah, we're totally at 4.7 now, but the width and height is not 0. We're just going to these smaller and smaller and smaller numbers. That's a problem. This happened because we didn't round. So 2.5, that is technically 5 divided by in half, right? But if we're dealing with pixel values, we cannot have a floating point here. We have to decide which side of that pixel the line falls. So what I'm going to do when I'm creating this child index here is this width. I'm going to say that the pixel in the top left is going to be in a 5 by 5. Let me actually draw out another thing here. In a 5 by 5, one of these is going to be 3 and one of these is going to be 2. I'm going to decide that this is the 2. This is a 2. And actually, this is going to be 2 by 2. Okay. This one is going to be 2 by 3. This one is going to be 3 by 2. And this one is going to be 3 by 3. Okay. So at this point, we now have 5 in every direction. At least we should. This might need to be 3 by 2 also, now that I'm thinking about it. I think that's right. I think this needs to be 3 by 2. Or 2 by 3, actually. No, that's what we had before. 3 by 2 or 2 by 3. Because the x coordinates have to add up to 5. And the y coordinates have to add up to 5. This... Oh, because the x is going that way. Okay, so this is also... this is going to be 2 by 3. Yeah. Because the x coordinates go this way. So we've got 5 going this way because of that first one. We got 5 going this way. We got 5 going this way and 5 going this way. Which means the ones here need to be the smaller ones and these ones need to be the larger ones. I don't know if that makes complete sense, but when I'm dividing that border, my top left corner here is going to be the smallest one. The top right one is going to be the largest one by 1 pixel. That should be okay. So that means my width and height here for my top left child, this actually needs to be the floor. What floor does is floor chops off that decimal and pulls it down to the lowest integer. Math.floor, math.floor. This one, the top right child, needs to floor the y, but ceiling the x. The x needs to go up to the next integer. Why? Because its buddy on the other side went down. And so to make up that gap, it has to go up. There always has to be basically what we've got. Let me see if I can draw a little number line here. 1, 2, 3, 4. So the smaller one is going to be here, and the larger one is going to be here. Who does this pixel go to? Well, it needs to go to the larger one because this one went down. It was right in half. This one went down to 2, so that means the other one has to go up to 1 to fill that space. Otherwise, we've got a pixel that doesn't exist in the system, and we can't have that because we just have tiny little lines everywhere, and it would look terrible. So for this one, this also needs to be math.ceiling, which raises the number up to the next integer. So if it's 2.5, it's going to go up to 3. This one needs to be floor, which if it's 2.5, it's going to go down to 2. Bottom left child, same thing but reversed. The bottom left child, its x needs to, again, be floored, but its y needs to be ceilinged because of that. So the x needs to be math.floor, and the y needs to be math.ceiling. The bottom right child, they both actually need to be floored, but here's the part that becomes interesting. This coordinate as well needs to have something done to it, because the current width divided by 2, that also needs to be math.ceiling, because the x coordinate needs to go down by 1. This height here, this needs to become math.ceiling current.height, because otherwise we're going to get a y that's in a fractional position, and we don't want that. We want all these to be numbers. This one, every single one of these is going to be a ceiling because it is here. It's the one that's got 3, 3. It pushes both of its siblings aside and takes up that space. So it needs the ceiling. It needs to grow up to the latest integer, the closest integer, in the x and y direction. So that, I'm just going to paste that on here. And here, and here, here, and here. Let's try that test again. The hope now is we shouldn't have any of these fractional numbers because that was what caused us this problem. Right? Let me just clear this. All right. Okay. Now that doesn't look as bad. Now I got 0, 0, 10, 5. We went to 3, 5, 3, 2. Remember, this is x, y with height. Maybe I'll change that a little bit better so it's a little clearer. Let's see. Let's put these in. Let's just use a template string because that's going to be a little bit better. Put these in coordinate pairs like that. And size is that, you know, that is a good point. I have had a probably not enough water today, but I have had enough food. But I appreciate you stopping in and saying that. Let's run this again. Okay, now we get a little bit more. 0, 0, size is 10, 10. Yeah, absolutely. I enjoy it. And hopefully we're not going to get into too much terribleness today. But we'll see. This is kind of interesting. This 3, 6 size is 1, 1. I don't know why that went into a different tree. That's kind of strange there. And I think that's because of the division and how it worked. That is, how does that have 4 children that are all 1, 1 if it's a size of 1, 1 itself? I'm kind of curious about that. I feel like this is going to be a problem. But let's take a look. Technically, if we really wanted to make this kind of foolproof without a lot of work, we'd make it so there was only a power of 2, because then it can be always subdivided evenly. But 10 is not a power of 2. This here is not the nicest. I don't particularly enjoy how this got printed out because it just gave all my children's tree nodes. I'd like to see a structure printed out in JSON. So I kind of want to add a print method onto here. Print, and we just print it as JSON, all right? Or like maybe get JSON. That's basically going to do something very similar to our current here, but this is actually going to recurse. That's just going to be the easiest way of handling it. I could do a dynamic programming for this, but you know, that's just going to be harder, and don't want to do it right now. So in order to do recursion, you have to start off with a base case and recurse down to that case and then come back up. So what I'm going to start off with is I'm going to make a helper function. I'm going to call this my getJSON helper. It's going to take in an element or a node. And what this going to do is it's going to say, okay, if, right? Well, let's just give it all its properties. It's going to build a data block. We're going to give our x is going to be our node.x, our y is going to be our node.y, our width is going to be our node.width, our height is going to be our node.height, and our value is going to be our node.value. And our children, we're going to leave it as empty for now. Then I'm actually going to loop over. Well, you know what? Do I want to go, because I have a choice here. I could actually map over the children to generate this array. I feel like that reduces the code readability, though. This actually needs to be an equals as well. I feel like that reduces my code readability. Let's just take a look at what that looks like. Node.children map child. Now remember, the map function is going to return an array, a new array, made up of whatever I return from these functions. And it's going to be called once for every element in the children array. To recurse, all I have to do, get, it's not this, get JSON helper, child. That's recursion right there. This actually doesn't technically need a base case. Normally you'd have a case up here that was like, if something break out of recursion and return value. I don't need that here because if I get to the bottom of the tree, I have no children, which means the recursion just won't even happen. And then I return data. So now I can just return get JSON helper current, and actually I can just call it this.root. And that will recurse through the entire tree, every single cell, building a JSON payload that slowly gets more complicated as you move back up the stack because the children array keeps getting more and more complex. Now I'm just going to do a nice print function here, and I'm going to console log. And so I could actually just say console log this.getJSON, and I'll show you what happens if I do that. All right. I'm going to change this now to tree.print. And if we run this again, you can see it gets down to this child array, and then it still kind of has the same issue where it doesn't nest appropriately. Now you can tell console log to kind of print out this, but then you have to keep telling it to go deeper and deeper and deeper and deeper, and I don't really want to do that. So what I'm going to do instead is I'm actually going to print out, this is a JSON string. So JSON object is going to be this.getJSON. And then I'm actually going to JSON.stringify JSON object, which we don't do very often when we're console logging like this, because normally console log takes care of the JSON stringify for us if we give it an object. If I do that, though, you can see it looks like crap. It does give me all the children, though. I have all the children. There's nothing that's just saying, oh, there's an array here. We're not going to unfold that for you. It gives me everything. There's a special way of handling this, though. In JSON stringify, if you pass it a spacer as the third parameter, not the second parameter, this parameter, I don't actually know what this does. I think it's an options array. If you pass it the third parameter as any number, it will do this. Pretty print. It will pretty print your JSON. And that looks a lot better. So let's see. We've got our width 10, x, y, width 5, 5. This one goes to 5. This one is 5. This one was the one that we recursed into. So let's take a look at this. We generated children for this. 5, 2, 2. This one is the 3, 5 and has some width of 3 and height of 2. Is that right? X of 3. That seems like that should be... That doesn't seem right. Because if this really is the 3, 2, that means that's this one, which means it's actually start at, let's see, it's going to be 5, 6, 7. So this one should start, this is where things get complicated. I kind of want to draw this out somewhere. I feel like this X should be 2 though, because if I take 3 and I add 3, I'm going to get 6, even though the width, this shouldn't be going beyond 10. So this will go to 11. So I think when we're creating our children here, this actually needs to be a floor. Yeah. And I think that makes sense, and I'm going to explain to you why. If we get here, right, this particular guy here, it needs to start. So this starts at 0 and goes 0, 1, 2. This one needs to start at 2 and go 2, or no, it needs to start at 3 and go 3, 4, 5. But if I do a width of 3 and I add that to 3, then I get 6. So if I do a width of 3 and I add it to 2, then I get 5. So I think that's how it's supposed to be. This goes from 0, 0, and 1, right, because 0 is counted on that. This goes 0, 1. This one needs to be 2, 3, 4. If we're doing 0 indexing. If we're doing 1 indexing, this needs to be 1, 2. This needs to be 3, 4, 5. But if you divide that evenly and this goes up, it doesn't work exactly the right way. I think that's I may be wrong about this, but I think that's going to work. Let's try to throw this into a visual, and let's see if we can figure that out. Maybe that will help a little bit. So what I want to do here is I actually want to build that same kind of what we did before. I want to build that same table grid. I'm going to do a 10 by 10 grid. And what I'm going to do is I'm going to declare a width up here and a height up here, and those are going to be constants. Maybe I'll make them changeable later on, but right now I'm going to make them constant. And then I'm just going to put in a table body. And then, this is where you get into a fun thing with React and JavaScript. I need to be able to do a map at this point, but I can't map over a number. Let's see. Is there a JavaScript way to just expand an array? I feel like there is, right? Let's just check it. JavaScript populate array of size. Basically, I want a range. Python has a thing like this. Python actually has a method that you can say range 0 to 10. And I could just do that, but I don't believe JavaScript has anything like that. And because Python does its loops kind of weird, it doesn't actually have loops that go over between two numbers. It has loops that go over a list. So you actually have to generate a list of numbers to map over. And you know what? That's not a terrible idea. Maybe we're just going to do that. So I'm going to create this. And this is going to be kind of inefficient to start out with. Export default range, start finish. You know, the fact that this keeps... That has to do with text nodes. I feel like that's something else. All right, what I want to do... what do you not like here? Export default, function. R equals here, and then I'm just going to do a standard for loop. I is less than, I is start, I is less than finish, I plus plus, r dot push, I, this probably actually needs to be equals, return r. No, it doesn't. Cool. Now I just have a loop that gives me a nice range. This may not be the most efficient way to do this, but that's okay. Import range from utils range. And then this actually just works now. Cool. Key. Or actually, let's just say item. Now we're going to return a table row. Inside this, we're also going to do another range. This actually should be height. Range from 0 to width. I'm going to change this to y, actually, just for the hell of it. Got map, x, and we're going to return a table cell. And in here, I'm just going to put x, y. Let's just see what that gives us to start off with. This is kind of a fun, quick way of just generating that 10 by 10 table. So I'm going to come in here. I'm going to start up my Vite server. There we go. Give it a minute. Okay, it's up. Let us... Actually going to pop this open in a guest window here, I think. Just so we have a clean slate. Let's go to our page. All right. So now what we see... No, that's not what I wanted to do. We have our cells. 0, 0, 1, 0, 2, 0, 3, 0, 4, 0, etc. all the way down here. Simple way of generating a nice table. So now we've got our console key. They're like, oh, there's no key in here. We could fix that pretty easily. Key equals. I went over keys in the last lecture or stream. I'm just gonna say row y. So anyway, if you're curious why we need a key, that would be the one to watch. Key equals column x. Oops, this is the wrong one. I do that, reload this, And now you can see that warning goes away. This isn't what we want, though. We don't want this. We want our actual tree structure to be visualized in here, right? So what I want to do inside this loop here is I actually want to get a value equals, and I want to get the value from the tree at a certain coordinate point. Which shouldn't be too hard to do because we're already kind of looping over that with our MJS. So let's actually create a new tree here. Let's say, and I am going to use a state for this. Well, you know what? Actually, because the tree needs to be modified and it's not creating a new instance of the tree, we should use a reference. Why? Because states are only useful if the value of the state changes. References are for objects that are unchanging, but pieces inside them might be changing. So I'm going to have a tree ref new, use ref new tree. And let's import that from there. Does that work? Oh, it did not like that. It says, hey, what is this? What is this tree thing that you're talking about? Oh no, it didn't like the value. Okay. I thought it was breaking on something that hadn't even broken on. That's fair. Let's do this. Tree ref current. The reason you have to do a current is because the tree ref builds an object. Object is actually current. And the value of current is going to be whatever this tree is. Let's actually give this 0, 0 with height. Tree.current.get xy. We're going to build this function in a minute. Okay? I just want to see how this breaks right now. Could we do this next importing non-existent modules? Let's just reload. Oh, okay. So the fact that it gets this far, tree.ref.current.get is not a function, that tells me that it was actually totally fine importing this JavaScript file and compiling it, which is cool. I've never tried an MJS file before, so I'm glad this works. Get. Let's go in here and let's make our get function. Not get JSON, but get xy. This is basically going to traverse the tree until it finds that pixel and give us the value at that coordinate. Right now, I'm just going to return 0 just to make sure everything else in the code works. Okay. I load this. No issues. I'm going to come back into app here. Instead of my actual XY, I'm just going to put value. There we go. And that's still the wrong one. And now you can see bunch of zeros. That's actually totally fine. Bunch of zeros is fine because that's what I told the function to return. Let's do something better. I'm actually going to need to duplicate a lot of this particular code. This code essentially helps me get to a certain point. So I'm actually, there are better ways of doing this, but I'm actually just going to copy this entire thing, paste it in here. Okay. I don't need to do child creation at this point. Okay. So let's say we get here. We found our pixel, set it and quit. Well, instead, if we found our pixel, return its value is what we got to do. That's the only difference here. We're going to actually return current.value. Here's a problem though. Oops. Every time. What happens here? What about these zeros? There is no pixel that matches these. So they'll just loop forever. In fact, this is probably looping forever right now. Oh no. Okay, it gets undefined. It doesn't like that. And the reason is, at some point we probably got a child index in here. And we're like, oh, there's no child index. What do we do if there's no child index? If there are no children and our child index doesn't exist, well, at that point, it means that we asked for a pixel in one of these larger squares. Well, we know that every single pixel inside that square is going to be the value of that square. So that's actually really easy. So if we don't have any children and we're trying to find a pixel color, we just return the value of the lowest level that we got to. Because we never got any lower, we never generated anything, which means the pixel can't be anything lower. So if we do that, if we say, okay, if current.children.length equals 0, then we're just going to return current dot value. And nope, I really just need to move this over here. That's what I need to do. Okay. Didn't give us anything at all. So let's add in that console log again. Let's go grab our console log from here because this is kind of a useful one. And let's just toss that in here. And let's also pull in our asking for X and Y. Let's just put in the pixel that we're actually requesting at that point. Okay, we reload. Okay, size 0, 0. Size is 10, 10, asking for 0, 0. It never recursed. It never actually recursed onto this. That's kind of interesting. 10, 10, size 0. Oh, you know why? Because we never added a pixel to it. That's why. This is actually completely legitimate. It shouldn't be recursing because right now there's the root node and nothing else. And by just what we just did is if there's the root node and nothing else, then we don't need to recurse anymore because we know that pixel color is going to be the value of the root node because that's the smallest we could get to. So then the question becomes, why is it not returning this value here? It should be getting down here, deciding the children is 0. Returning. Oh, you know, I know why this is. And this will explain it. Oh, value is not... Right, returning current dot value. Null. You know why it's null? I'll show you. Because when we create our root node, we create it with a null value. So that means we should actually put a value in our tree so that we can start off with an initial value to put into our root node so that something actually exists there. Which means that here, when we create our tree, I want to create it with 0. That looks more like it. This is now actually pulling from that tree. Now it's called add. Okay. So what I'm going to do in here is I'm going to create a button. Button. Add pixel. On click, and the reason I'm doing this is because I kind of want to control when this happens so that I can be ready to look at logs and things like that. This is often very common. If you have something that's going to set off a chain of events, you put a button on it just so you can be ready to observe what's happening. Otherwise, it may happen too quickly and you say, oh, I wasn't ready. When the page loaded, it did the thing and my inspector wasn't up. So, tree ref.current.add x, y, and value. Let's add 4, 7, and put a 1. And then let's see what that gives us. If I click add pixel, did it do anything? Oh, the whole thing froze. Because now I can't click it again. So something got stuck there. Okay. So let's go ahead and debug that through. If we get into add, let's open up this console log. And then let's take the one out of here because it's just taking up space. Oh yeah, you can see this is what happens when you go into an infinite loop. Your thing will just spin forever. So what we actually need to do there, open a new tab and kill this one. If it won't go away, you can also right click and open up the task manager, which brings up the Chrome task manager, and then you can actually delete tabs from there. It's kind of annoying. I definitely don't like when it happens because it means I have to open up a tab again and get everything set up right. Add pixel. Oh, that's interesting. Look at that size. That size is 0. And you can notice how much that's happening. So, why did we recurse on this? 4, 6. This was the problem I thought we were going to run into. Because we actually gave it, in our app here, 4, 7. Here. So why did that work here, but it broke on the other one? Well, let's take a look. If I go ahead and I run that test code again. Ah, we've got a not a number. That's interesting. Okay, so let's try to find the top of this. Here we go. 10. Size is 10, undefined. What is that? That is from size is Oh, our height is unset. Oh, that's because we screwed this up. We didn't put a value in. This was expecting 4 parameters or 5 parameters. I gave it 4. So it just scooted them along and said, oh, this value XY width, it didn't have anything for height. So it just set it to null. That's exciting. Let's try that again. Okay, you're still running. Cool. So size is 10, 10. Size is 5, 5. Size is 3, 2, 2, 1, 1, 1. And this is the thing. Why didn't this trigger? 4, 6. Size is 1, 1. Oh, because I passed 4, 7 into it. So this, we picked somehow the wrong child. And you know, I think I know how we did that. We recursed into the wrong child. That's basically what happened here. We should have gone into 4, 7 because the size is 1, 1. There was only one child to go into at that point. We went to the wrong child, and I think that's because of our current height here. So let's actually take a look at this. Let's say, let's put another console log, and we'll say, we are looking for X and, oops, this needs to be a, and Y. Below halfway, halfway Y, below, and we're just, basically, this is how I debug this stuff. I just do prints. I print stuff out because it's very useful to tell you what's going on. Below halfway X, below halfway X, and I think this will tell us something valuable. Oops. Run the code. Clear it very quickly. Okay. We are looking for 4, 7 below halfway. Let's just skip down to where it started repeating. Okay, so 3, 6. We're looking for 4, 7. Below halfway, false. Below halfway, X, false. And we ended up here. I think this below halfway Y should have been true. Because if it was below halfway, no, actually. Below halfway Y is false, which means why did it pop to this and why didn't it pop to 4, 7? Because this is only, oh, so the problem was somewhere else. This is only one tall. If we hit 5, 5, okay, we're looking for 4, 7. Halfway Y is true, which means we are looking, we hit something, it's 2, 5, and this size is off now. Because these are 5s, this should be 3. Shouldn't it? Because so we got 10, 10. That's 5, 5, and this should be, this is the X. So it's the left side of our screen, but also the bottom side. So this is the one that we're grabbing. So that should be 2, 3 of it as its size. But instead, we're getting 3, 2. And it's also 2, 5. So the Y looks correct. The size does not look correct. This also should be is very much the wrong child though, right? Because if we're above the halfway Y, then we should be hitting child 3 or 4. Which means that none of those children should actually have a Y coordinate of 5. They should have a Y coordinate of 7 because this Y is going to be 5. So they should be jumping up. Somehow we're actually getting 2. We're getting position 2 when we should be getting position 3. So how is that happening? Are we creating these wrong? Okay, so what we're basically looking at, we hit this, so this is our problem right here, is in between these two. So when we go from here, we're at 0, 5, which kind of makes sense, okay. So if we're at 0, 5, that means that we are in the first X. So below halfway Y is false, but halfway X is true, which means that we're looking at this cell here. X and Y. So this is 5, this is 0. That's fine. So we're in this third cell. Then we get the halfway y true and the halfway x false, which means we're looking at this cell. Halfway y true, halfway. Is that accurate? Let me draw that out. Because I feel like I need a little bit more visual in here that I'm not getting. Okay. So this is 10 by 10. This is our 10 by 10 square. 10 by 10. So that means if we subdivide it, each of these is going to be 5 by 5. So you guys are watching me struggle in real time. This is actually how coding works. You run the problems and you try to figure it out. So first of all, the first thing we're doing, where is my term? We are going to halfway y false, halfway x true. Okay, so it is below the halfway x. It is not below the halfway y. So it is below halfway x. So it's here, but it's not below halfway y. So it's this one, which is kind of interesting to me because the coordinate we gave it was 4, 7. This is the one it should have picked, actually, not this one. And I think below halfway y, am I misreading what these variables do maybe? So, okay, so the y is less than that. X, no, that's totally it. So at this point, below halfway y is false. So we know that we are in 2 and, or no, we know we're in 3 and 4. That's what I was reading wrong. So we know we're in 3 and 4. We know we're in one of these two. So these two, we're going to use red for the ones that we didn't hit. These two we know we didn't hit. Then we look at our below halfway x. That is true, which means we're in group 3, which means we skipped group 4. Okay, so then we go ahead and we subdivide that further. Each one of these is going to be 5 by 5. Okay, so we got 10 by 10, which we split. These are all, oh no, these are each 5 by 5. But each of these individual ones is actually, this is 2 by 2. This is going to be 2 by 3. This is 3 by 2, and this is 3 by 3. Based on this grid here. So at this point, we've figured out our cell here. We're at this number 3. We look at it again. That's 0, 5. That makes sense. We say, okay, below halfway y, true. So we are looking at 1 and 2. So we know we're going to skip cells 3 and 4. Below halfway x, false. So we are in cells 2 or 4, and the only one available to us is 2, so we're going to go into that one. This one, this particular cell, is 3 by 2. It's supposed to be anyway. So I'm going to go here, and I'm going to say 3 by 2. It is 3 wide and 2 long. Is that what we're actually getting? Yes, we get 3 by 2, so that's totally fine. Now the question is, what coordinates does this handle? Because we're looking for 4, 7 at this point. Does this look like this is where 4, 7 would belong if we had 10 cells here? 4, 7, okay. 4 definitely belongs in this side, 7 belongs in this side. 7, 4, let's see, 4 and x. Probably, I would say actually belongs on, oh no, it does belong in this side because if we're talking about in between 0 to 5, 4 is definitely on this side. And 7, if we're talking about between 5 and 10, 7 is technically right on the border of that. Now here's the interesting part. 7 be right on the border of that means it's actually technically in cell 4. It should not be in cell 3. Because this one takes up that border. 7 is, well, technically 7.5. If you're looking at this cell, this is actually 5 and 6. This one should be, oh no. Should this be, this border is 5. I need tally marks here. Because this one is going to be 1 through 5. Okay, so this is 6, 7. But 7 is on the borderline here. So 7 is actually going to be 7, 8, 9. And 10 is this borderline. So 7 actually is supposed to be here. We're actually looking for this cell right here. But we ended up in the wrong chunk. And that's why we started having problems, because we ended up with 4, 6. 4.6 is the highest we could possibly go. This is 4.6, this one right here. So this is 4.6, this is 4.7. We don't want this one, but we ended up choosing the wrong child to go into. The reason for that, I believe, is because this one, that current height and current width. So then the question becomes, does this need to be made into a ceiling or a floor? Because we definitely ended up at the point where we took that current height divided by 2 and we got 2.5. Just like we fixed earlier in the stream. So that 2.5 here, and again, if anyone has questions about anything I'm doing or is super confused, please just put it in chat. I definitely want to make sure that y'all understand what's going on, and I can explain it in a deeper level if you don't understand. Even if you're like, I don't understand literally anything that you're doing, I don't mind taking 5 to 10 minutes and doing a full rundown of what we're actually doing again. So this is 2.5 below halfway, which means this is supposed to be that borderline. And that borderline skews downwards. So I think this needs to be floor. Yeah, so let's floor that. I think that's because we determined that those borderlines skew to floor. So I think we need to floor that. Let's try this. Clear that again. Oh, okay. So that didn't crash this time. 0.5, so I see now it hit 2.7. We're looking for 4.7. It jumps to 3.7, which has a size of 2 and 1, and then it picks that 1 on the other side, and it goes, oh yeah, you're 4. Cool. There we are. We're good. What if we reload this? Oh, you know what? It's still infinite looping because I just left it running. Now, if I open up our task manager, you can see there's our tab, infinite looping, taking up all my CPU. So I'm going to end that. And what that's actually going to do is that's going to completely kill the tab. So then we're going to come back here. We're going to inspect. Go to our console. Let's hit this again. Oh, site refused to connect. Am I not? You know what I did? I stopped the beat server. That's why. I stopped the build server, and so it's like, hey, I don't know what you're talking about. There's nothing listening on that port. Okay. So if I add a pixel, I should get a 1 somewhere in here. Okay, size, we're looking for this. Now here's the great thing. We did add this pixel. It didn't re-render. Why didn't it re-render? Well, it didn't re-render because changing a reference does not cause React to re-render the project. So when I called treeref.current.add here, that data's changed. It's up to date. But it won't re-render because I never told it to. There is a way to actually do this, and I'm going to add in what's called a force re-render hook. Okay? And let me show you what that is. Use render. It's very simple. We're going to import use state from React, and we're just going to export a function. And all this is going to do is it's going to have a state, and then update set render count equals use state 0. We're going to turn a function that whenever called sets the render count. You know what? I do actually need the count here. Render count plus 1. How does that work? Well, we're not using this value for anything at all, but React doesn't know that. And anytime it sees any change in the state, it knows it needs to re-render the components that rely on that state. So what I'm doing here is I'm just saying, hey React, this state changed. And React said, oh shit, I better re-render the program then. It didn't have to, technically, because nothing actually relies on this variable, on this value, but React doesn't know that. So if you need to force a re-render, this is actually a pretty common way of doing it, is you just increment a value. Because the number of times you do need to force a re-render is usually pretty low, which means you can increment this value for a really long time before you actually have problems. What'll actually happen is if you increment it something like a trillion billion times, it'll actually flip over, go negative. But that doesn't matter. React doesn't care about that either because it's still changing and it knows it's changing, so it needs to re-render. So this will just basically allow you to re-render whenever you want, forever. Which is very useful in a case like this where we have a reference that won't automatically re-render. So I'm going to say import use render from utils. Now you notice all these things are going in utils. That's because these are specific functions that I might want to use other parts of my program. They don't belong to app. I might want to use render somewhere else, so I put it in utils so that it's available. And then I'm actually just going to say const render equals use render. This is a very common if you're making your own hooks in React. You put use in front of them because use ref, use state, etc. And then you can return whatever. You can return a function. You can return a value. You can return whatever you want. In this case, I'm just returning a wrapped function that handles this state. If you are not using other hooks inside your function, like example in range here, I did not call this use range because there's no need for it to be a hook. Hooks have to be treated a certain special way in React. They can only be called at certain points in the lifecycle of the component and at certain parts in your code. So making something a hook, you usually only want to do if you're utilizing another hook, like use state, what we're doing in here. Anyway, I'm pulling out render. I'm calling it here. So now whenever I click this button, it's going to call this function, and then it's going to trigger the app to re-render. You should not do this unless you have to. It's very dangerous to fully re-render your app because React uses the state to render only pieces of your app. If there's only a piece of your app that uses that state and that state changes, React only renders that piece. In this case with render, every single place I'm using use render is going to re-render when I call this function. It's going to be less efficient, so you have to be careful with it. In this case, it's okay though. All right, so let's go here, add pixel, and now you can see, it's kind of hard to see, but there's our one. Let's do something a little bit better. All right, let's make a color map. Equals, and I'm going to map value, so I'm going to map 0 to FFF. Let's make it blue. And I'm map 1 to a green value. Make it like, there we go. Now, instead of my value here, I'm not going to put a value. I'm going to make my table cell have a background color based on that color map. So I'm going to add a style parameter. Remember, React styles are objects. So I'm going to put a width of 10, height of 10, and a background color. And remember also in React, you can't use the dash color because in JavaScript that means you're subtracting something. So instead we use a camel case, and then React knows it needs to convert that into a dash. It's just smart enough to do that. I'm going to say color map index by value. Now when I open this up, reload, you can see they're all blue. And when I add that pixel, it turns green. That's pretty cool. That is pretty cool. So let's take a look. Let's go in here. We've got all that. We got our background color set up. Let's make it now so that it's not just this button. It's when we click on this, it sets a specific pixel. That could be kind of fun. So I'm going to get rid of this. Well, I'm going to leave the button for now. I'm going to add an on-click listener to my table, to my TD here. And I'm going to take in this current here. Okay. TrueRef.current.add. And instead of the 4 and 7, I'm going to use X and Y. Where did X and Y come from? Right up here. Those are our coordinates from our range loops. So we already have our X and Y. Get rid of this button. And now, oh, I didn't put the render. Gotta add that render or else it doesn't know to change. So now I click. Oops, what is it doing? There we go. Oh boy, it's all sorts of stuff is screwing up here. That's not what it was supposed to be doing. So let's say I clicked here. That kind of showed up, but it was one above where I wanted it to be. Let's see if I click in the corner here. That works. If I click this corner, that doesn't show up at all. Let's take a look. We're looking for 90. We go to 50708090, and that should set it, right? But it doesn't seem to set that in here. Well, that's kind of interesting, isn't it? We almost need to be able to view our tree at this point and see what's going on, because that definitely should have... What if I go here? 8. Here. None of those actually work. This one actually goes one below where it's supposed to be. So definitely our tree structure seems to be a little busted here. It worked for that particular one. Well, this one here. But if I do that, all 3 of these open up, which is these 2 open up. So that's quite strange. Right? Like that definitely should not be what it's doing. And I suspect part of that is because we're ending up with these things that are like not exactly the right size. But anyway, let's take a look. I want to get rid of that console log also. Where is that? It's in the get. There we go. So I'm going to actually call my get.json on this tree. And I'm going to use that to print out some actual data on what's going on here. So let's actually call JSON tree ref get JSON. And for starters, I'm just going to print it out. Okay, I'm just going to say the same JSON stringify that we did before, null and 4. Okay, and a fun thing you can do. This is not quite going to work, and I'll show you what it does. TreeRef.getJSON is a function that's accurate because it's supposed to be TreeRef.current. Okay, that's not showing particularly nicely. Let's say if I go here, that's not showing real well, but I did the pretty print. And if, in fact, if I look in here, it's got a bunch of new lines in here, but the browser doesn't respect new lines normally. What it does respect is if you put it in a pre-tab or tag. And what pre tells it is whatever I put in here is pre-formatted. So use its formatting rather than what you think it should be. And now you can see we have that nice visual here. I actually want to make this grid smaller as well because it's just kind of large. Let's make it a little bit tinier. Yeah. Now, let's see. What if I click on this cell? You are a little late, but that's okay. You're here now. If I click on this cell, it sets the wrong one. So what happened here? We got our children. All right, 3 by 3. That's okay. This one is 3 by 3. What's our other 2 children? These are all 3 by 3, which makes sense because 6 divides evenly into 3. So let's take a look at our next one. This has 3, 0 and a width of 1 and 1 because we have that 3 and we're dividing it and taking the floor. So we have that 1, 1 and etc. Okay, so we check out here. This one has a width of 2 and a height of 1. And which one did it actually set? It set this particular one. We clicked on 5, 0. That's right, 5, 0. This is 5, 0. Somehow we got 5, 1. That's not what we expected. So in this particular tree, we've got a 3, 3. We go down to this child that is 4, 0. So this starts 0, 1, 2. This starts 0, 1, 2, 3, 4, 0. And it has a width of 2 and a height of 1. So it goes here. Width of 2 and height of 1. Wouldn't that technically mean it's just these two? We should be looking at 5, 0. Why didn't we get 5, 0? So this got split into 3, 0. So this is a 1 cell. This half, so it got split into this 1 cell. It should have gotten split into these 2 cells and this 4 cell. All right. So actually, let me just print screen this. Or maybe I can take a snapshot. Nope, my snapshot's not working. let's go here. Let's get another paint window up. See, MS Paint. MS Paint is amazing. I'm just going to snapshot this and grab this little guy here. All right. So we can play around with it a bit. So what we're looking at is we're looking at these cells, okay? This is the one that was chosen. The rest of these were not chosen. And so if I look at my code here, it subdivided these into a one cell, which was what exactly what it was supposed to do. And let's just use these 4 colors on the bottom. So it should have subdivided it into these 4 cells. This is how the subdivision should have gone. Did it do that? Well, let's take a look. It 3, 0, and it did a 1 but y1. That's this cell, so it did that. The next cell is 4, 0, and it's a width 2 and a height 1. Okay, width 2, height 1, 4, 0. That looks right. The next one after that is 3, 1, and it has a width of 1 and a height of 2. That seems kind of weird. 3, 1. So we're looking at 0, 1, 2, 3, 0, 1. Oh, no, it has a height of 2 and a width of 1. So that's totally fine. We're good. The final cell is 4, 1, and has a width of 2 and a height of 2. So 0, 1, 2, 3, 4, 0, 1, and it has a height of 2. That all evens out. This was divided appropriately. It then decides, if we're looking for 5, 0, it picks this one. Why the hell did it do that? It should have picked this one. Because this is the one, this is the cell. Well, 5, 0 actually is this cell right here. Oh, so it did pick the right one. Okay. 5, 0. Okay, so 4, 0. Now here's the problem we end up in. We have multiple children that match here. That's kind of an issue, isn't it? So this child technically doesn't match, right? Because it's not 4, 0. This child does match. Their heights are both 0. So we're never going to do anything with them. This child, it says, oh yeah, 4, 0, 1, 1, that doesn't match, but this one does, so it sets the value there. That looks right. That's the second one over, and it's at the top. So that is supposed to be this particular cell. So why did this one show up when I asked for that? When I asked to get this particular cell, when I asked to get this one, it showed up as wrong, and I think that's probably because... Oh, you know why it is? I bet I know why. Because when I set everything, I did this current width, current height stuff on it. Forgot to do that to the get. So the get was still using the 2.5 or the half chunks. Actually be thirds in this case. So I think if we put a ceiling on that. Now you notice this is why the cardinal sin I'm committing here is I'm copy pasting complex blocks of code. This code is almost identical to this code. So if I get a bug in this code, it's very likely I have a bug in the other code as well. So that's why if you use something more than twice, or if you use something once that's complicated, you probably want to put it in a function. Now if I run this, oh, it's still showing up in the wrong place. Okay, well let's take a look at that then. Let's go back into our test code here, okay? And let's make this exact same tree, 6 by 6, and we're going to set position 5, 0. All right? And then let's get 5, 0. And let's just see what we get there. Because for some reason we're getting 0, and we should be getting 1. So I'm going to make a new tab here because I don't want to kill my build server. And we're going to go into, I forget, it's Quadtree. Now, let's run our utils, test. Okay, it gives me 0. This all looks right. This got put in there. My tree, I know my tree already looks correct. So what I'm going to do is I'm actually going to take out this console log. I'm going to grab this one because this might be useful. And I'm going to uncomment this one because this is the one in the get. And I want to see what's happening here. Run that again. So now that's the get. Okay, size is 6.6. We're looking for 5.4. We go into 3.0. Okay, that makes sense. 3.0, size is 3.3, asking for 5.0. We get this chunk. So that's currently correct. All right. Oops, not this one. Okay, we jump down. We jump down to 4.0. Okay, 4.0. Size is 2.1. Looks good. We get to 5.0. Size is 1.0, asking for 5.0. That's kind of interesting, though, because I wonder what child index we actually hit. Because remember, we have 2 5.0s. And one of them is 0 and the other is 1. And somehow we're getting the wrong one here. Let's take a look. Log. Dot child index of child index. Let's just run this again. Oops, not clear. Okay. So we get child index of 1. That's this particular one. That's cool. We get child index of 1. That's here. And then we get down here. We get child index of 1 also. I think that's where our issue ran into. Because this is child index of 1. This is the one that we actually picked the previous time. So now I'm wondering, why did we pick child 4 when we set, but we're picking child 1 when we're getting? Something about that code is still off, which what I want to do then, oops, is I want to put this same check in here. Okay, so let's do our add. Okay, let's run this again. Okay, so here's our add. All right, I think it comes to here, yeah. So we get child index 1 in our add. Okay, child index 1, which is fine because we get here. Then we get child index 3, which is the correct child index. That is the one, well, maybe it's not entirely correct, but that's the one that we want. We got that child index 3. In this case, we only got child index 1 again when we were supposed to get 3. Why is that? So we got child index 3 here. Below halfway y is false and below halfway x is false, which means we're in that upper corner. In this case, below halfway y is false, below halfway x is true. Why is that? Well, this is the wrong one. We're looking at this one for that index 1. So below halfway y is true. Below halfway y. These should be using the same thing. So I'm just going to copy this. Maybe one of them I typed it in wrong. Because those should be the same code. I mean, they look the same. Let's try that again. Okay. Oh, now they both give 3. Okay, so I just copy pasted it wrong. I must have. What happened there? What changed? Okay. Let's just paste that down there and see if I can find a difference between them. Current.y. Oh. These I put as both floors and these I put as ceilings. That's all the difference in the world. So these ones I've done as floors. Which, yeah, I remember why we did that. So this again is illustrating why you should not duplicate code like this. Because it does the wrong thing. Let's go back here. Let's see if this works now. That works now. Does that work? Hey, look at that. These all work. And you can see these trees getting slowly more populated as we go on. Now, here's the thing. If I fill out this entire block, that doesn't need to be a a tree anymore, right? So let me actually just go in here, reload this, and let's fill out that entire tree. We don't need this whole tree to be so complicated at this point, do we? Because it's all going to be one block. And so the whole point of this algorithm is that we can do stuff like this. We can have that cheaper storage for this block that's all been set. So what we want to do is we want to almost have a collapsing algorithm on this. So as we put in this and make this all green, all of these children should collapse into one child because they all have, well, let me see. Children, okay, this one, this particular one, this has value 1, this has value 0. Oh, but yeah, so these two both have value 1 because it's a weird setup. These ones have value 1, and all of these do. So all of the gets, all of the things in here have that value of 1. So the problem we run into, though, is how do we do that? In this particular case, we say, oh, we could look at every single child and determine if it's that value. Can we, though? Because this child has a value of 0 and this one does too, because these are duplicates. So maybe what we should do first is we should try to eliminate these duplicates. And there's a couple ways we can do this. So this particular one, this is a 1, 1. We don't need to worry about duplicates here. This one as well is a 2, 2. That's fine. The only time we need to worry about this, really, is if we end up with this particular situation, I think, where we've got a width or height of 1, so that it's doubling up with all these, because it has to be at least 2. We're expecting at least quadrants. Can we collapse this? Probably, but if we collapse it, we're going to massively screw up our indexing here, because the indexes are picking the last ones. So do we want to do that? We might be able to. How would that work? Because we've got 2 instances where this is the case. We've got here where these are collapsed and there's only 2 of them. And then we've got here where they're collapsed and there's only 2 of them. We have 4 nodes in this case, but we want to only have 2. We could actually do something a little bit different, though. We could say, okay, we set this point. We went through these current nodes. Let's do a cleanup step on them. And then we could actually just call the get method, or our specific get method on them, and figure out if all of our quadrants are covered. But I feel like the children thing is going to be a lot easier to deal with, simply because, yeah, it's just going to be a little cleaner. So, though actually, no, I'm thinking of something else. We can't do that. So how do we collapse these then? Whoops, I didn't like something that I just did there. Oh yeah, okay, that's reasonable. This one in particular, these 2 children should not be there. They're duplicates. But these later ones are the ones that we're going to actually be using. Indeed. Well, what we could do is we could first force our system to use these first ones, these early on ones. Because if we can force it to use the early on ones, then we can actually just use a set and kind of check duplicates and be like, oh, do we need to do this? Do we need to do this? No, we don't. So let's not do it. So that's a thing that we could do. And again, this only happens in these 2 specific cases. Oops. These cases where one of them is 1 across and the other one is, I guess it can never happen in 3, can it? Because the 3 can also be subdivided into 2. Oh no, it could, because that could, yeah. So any amount, any shape that ends up with a single dimension being 1 runs into this problem. But only if both dimensions aren't 1, because if both dimensions aren't 1, then it's a terminal node and we never go any further. So in this case, we're fine. In this case, we're fine because we have those quadrants. It's only if we can't divide the thing evenly, which means one of its dimensions has to be 1. So let's first of all just kind of detect when that happens. All right. So when we get into, let's look at our children creation first. is special. I'm just going to say is special. Current.height equals 1. Or current.width equals 1. If, and then if we have to create children, we're going to say, okay, if is special dot log creating special. This will just let us know if we can even detect this appropriately. And now I actually want to run this code. Pull this out as well so I can know when it's actually happening. Nope, not there. Okay, so 0, 0, we go 6, 6, 2, 1, and then our 2, 1, we say create special. Totally fine. That's exactly where we want to do it. Now, the question becomes, if we have 2, 1, right? So 2, comma 1, that is going to be, that's width and height. So that's 2, comma 1. Or no, this is 2, comma 1 here. If we have that, then we want to squash our second ones. And actually, we kind of want to make a translation, don't we? Because in that particular case, if 3 and 4 don't exist. So 3 actually maps to 1 and 4 maps to 2. So in that case, we can say if is special. Oopsie. Then our child index 3 needs to map to 1 and 2 needs to map to 0. That doesn't seem right. Wrong one. 3 needs to map, so 2 needs to map to 0 since these are 0 indexed, and 3 needs to map to 1. So basically they need to subtract 2, but only if they're above 2. So if in the case of 0 or 1, we don't want to subtract 2 because those are already in that top row. Right? They are actually all both the, oh no, that would be this one. Below halfway. No, they're both below halfway Y. That's why, because they're both in that top row. So these bottom 2 need to be translated. Actually, you know what? We could do something smarter here. We could say if we are a special, particularly along the height, so if our height is only 1, we know that there can never be a below halfway Y. Because below halfway Y is these 2 cells. If we only have a height of 1, these 2 cells are the only ones that can exist. So below halfway Y, by default, can only ever be true. Or false, sorry. So I'm actually going to say if current.height equals 1, below halfway Y equals false. That'll do it. And what this does now, this is going to fuck up this thing. But now if I click here, oh, is special is not defined. Yeah. Let me get rid of that for a minute because I didn't actually want to put that in there. All right, if I go here, I now can see, I go down here, children, okay, children. This particular one now, it set, oh no, it still set its value here. Oh, because that was the X, not the Y. But this shouldn't exist. This particular one should never exist, so we never should get... we never should get into that position. I always set this to false. Maybe I did something wrong with that. Let's just take a look here. Click this. Okay. 5, 0. Below halfway 2. Okay, so here's where we get to that here. Below halfway Y false, below halfway X false. And now, for some reason, it still picks this particular value, which is the third one. So below halfway Y false, below halfway X false. Oh, I have it backwards. It should always be below the Y. That's why. That's why it's screwed up. Okay, let's try that again. And now it doesn't show up there, which is fine. Oh, no. Now it's infinite looping. Oh no. All right, what has happened here? Why is that happening? Okay. Let's just go into our test code again and see if we can figure out why it's happening. This is why it's very useful to have test code. All right. So now I've got my tree in there. I'm going to run my test code. All right. Yeah. Stop. Oh boy. I'm trying to kill it. It won't die. It won't die. It's alive. Frankenstein's monster. Okay, seriously though. I need you to stop doing what you're doing. Or at least it seems like it's stuck anyway, so that's probably fine. It's probably because this is taking up all the CPU. Bring me my task manager. Come on. Oh god, literally the entire browser locked up. There we go. Give me the task manager so I can kill the other tab. This one, yep, end process. And that one, end process, cool. Okay, now that ended. So let's see what happened. Okay, we're looking for 5-0. Let's pull this a little bit over. No, that's not all what I wanted to do. Thank you. Yeah, I want you to be there. Let's bring up our screen here so we can kind of check that. So we got to, we're going to 5-0. No, this is giving me the pencil. Our size is 3-3. Okay, so this is fine still. Now we hit this, size is 2-1. We're looking for 5-0. Oh, that's why. Size is 1-0. That's why I didn't like that. And because the reason is in our tree, our previous tree system that we had, which I've now lost, we had those 4 cells, right? Well, one of those cells had a height of 1-1, and this one has a height of 0-1. So what we're actually going to do is let's modify this code a little bit and say we're looking for current x, current y, width is 1, height is 1. So let's actually say less than or equal to 1. So that way that'll still let that loop break, because if we get to a 0 height or 0 width, we've probably actually still found the cell. It just doesn't think that it deserves a height for whatever reason. So let's try that again. Pull this in there. And if we run that again, okay, we get all the way there. That's fine. This is fine because we actually need to take this code and move it all the way down here to our get, because we're basically doing the same thing here. We can fix that. I'm not going to do it right now. Now let's see if I run that. Uh-oh. Yep, that's constant. Constant variable. Now I get that 1 back. That's what I want. See, this is why it's useful to have a test case, because now I don't have to make my browser hate me constantly. Okay, I need you to give me the developer tools, please. Thank you. All right, let's load that again. All right, there we go. Now, the only thing we've accomplished is now it's using these appropriate things right here. Okay? That's fine. Because now what we can do is we can make sure that these don't get generated at all. Because that's what I'd like. I'd like to make sure these don't get generated. The original reason we're doing this whole thing is so that we can eventually collapse these when they don't need to be children. So like if I do this one as well, at this point, these 4 children aren't needed, right? I could set this value to 1 and get rid of them entirely, and I would still have the same effect. That's the whole point of the Quadtrees. We can compress that data storage, and right now we're not able to do it. So now that I'm using the first children in the array, or in the list, I can now get rid of these ones and not generate them. So that's in here when I'm generating my children. Top left child, top right child. Bottom left child. Do we want to generate the bottom left child? If our height is 1, we do not. If current.height is greater than 1, only at that point do we generate the bottom at all. Let's actually just do that as separate. If current.height is greater than 1. So these children, now we're technically not doing a real quad tree anymore, because a quad tree actually has 4 children. But when we're down at this low level, we don't want 4 children anymore. We only want to have 2 because it doesn't make sense for us to have 4. Get rid of this task manager. So if I load this again, now you can see there's only 2 children here that have that value. Cool. If we do this one, though, this one still has all 4. And this one actually is getting... This value is cool. This one shouldn't be there. And in that case, this one shouldn't be there. So this is the particular 1, 2, 3, and 4. Let me see. This is, we don't want 2 and 4 at this point. We're okay with 1 and 3. We don't want 2 and 4. And that's why if you look here, 1, 3, 2, and 4. So 2 and 4 are now being set. So we have the same problem as we had before, but now it's, instead of these top ones being set, it's these right ones being set, and we want the left ones to be set instead. So we're just going to do what we did the time before. Change this, and we'll say if current.width is equal to 1, then the below halfway x has to equal true. Change that to a let. We're going to copy this. We're going to come down here because we need the same code in our get function, otherwise it won't get the value appropriately. And now we'll come back here and we'll just run our test. But in this case, we need a different coordinate. We actually need to be trying to set one of these. So let's try to set, what is this? 0, 1, 2. This is 0, 1, 2, 3, 3, 2 is what this is. So let's try to set 3, 2 in our test code and make sure that we get it back. Okay. So we're going to set 3, 2, and we're going to get 3, 2. Run that code. Did I not save it? Oh, it's in there twice. Okay. 6, 6. We go to 3, 2. We hit 3, 3. Let's actually check this again, right, against our image, just to make sure that we're doing the right thing. Okay, so 6, 6. We get this whole thing. We get the top 3, 3. That's fine. We go to 3, 1. Beautiful. Size is 1, 2. Then we hit 3, 2. All right, let's test it against here. Let's make sure that these are the appropriate keys. These are now getting the, well, that one is anyway. This one is still wrong. Why is that? We're getting the right one here. Yeah. Oh, no, because 1 and 3. That's the 2 we want. 1 and 3 is totally fine. And that's good. The issue now that we run into, though, is we're looking at 1 and 3. We can't get rid of this one. We can't. It has to be there because otherwise it'd be 2. So our map here actually becomes a little more interesting. In the previous one, we said, well, 3 goes to 1 and 4 goes to 2. We've got kind of a similar thing, right? Where this 2 needs to go to 1 and 4 needs to go to 3. But in fact, 3 is actually going to be 2. Because we're only going to have 2 cells. It's just they're going to be vertical now instead of horizontal. So if I go in here now, let me actually just pull that in. And I'm going to do the same thing that I did before. I'm going to say, okay, the top right child, we're only going to do if our current width is above 1. Okay. Same principle, right? We want to get rid of 2 and 4. So this is 1, 2, 3, and this one has both conditions, or, well, and current width is above 1. So now that means this cell we always have. This cell we only have in some cases. In some cases, this one we only have if we've got that good 2 by 2. If I come in here now and I try to set this, the whole thing just dies. It's like, what? I don't know what you want from me. I got so confused. Yeah, it just explodes because I tried to make it access an index that didn't exist. And that was probably actually in the get here. So what I need then is in the case of the current width being 1, this particular fella needs to actually go to 2. So I'm going to say if current.width is above 1, else child index equals 1. Or, yeah, it needs to go to the second one. That might work. I think it might also... No, it still breaks. This is a funny way that breaks, doesn't it? It breaks without any console logs, which is... I really do not appreciate it doing. Let's just do this. Let's console log in here. Console.log current.children. And let's see if this will help us figure out why we're hitting that point. Oh no, because this is in the add, this is breaking. So I gotta go here. Console.log child index current.children. The fact that this is breaking without giving me any logs is actually really irritating me, because that's not how this is supposed to work at all. Like, I know React is actually kind of exploding really hard. That's basically what's happening. It's exploding inside a render cycle, and so it really doesn't like that, but it should still be giving me at least the logs of what's going wrong. Well, let's just use our test then. All right. Let's use our test, because there we go. That'll explode in fascinating ways. Okay. This is mechanics of 1. Here's the second one. Here's the problem one. Okay. We're looking for 3, 2, below halfway. We get down there. We get down there. We get into this one, 1, 2. And we have an index of 2. Oh, so it's the 2 index. What is that one? When do we hit 2? We hit 2 when we are below the halfway x, but not below the halfway y. So that is actually this particular one that doesn't exist. And that one, we shouldn't even be able to hit. Because... Oh yeah, that's why. Because below halfway x, we are below the halfway x. So we're over here, but not below the halfway y. So that becomes this one. Right, which is 2. And that actually needs to become the 1. So this, where I had that special code in there for the 3, that actually belongs in here. If current.width is above 0, or is above 1, else, in this case, we only have 2 elements, and 2 needs to map to 1. Child index 1. Okay, that I think is the issue. Let's try that again. I actually want to get rid of this now, because it is causing me problems. All right. We got our insert. That went fine. Now we're doing our other... The get is now broken. So that's completely fine, because we need the same code there. So this code, you can see we duplicated a lot of code and we're moving it between stuff, and it's starting to cause problems, because now we have to put it in both places. Let me take that out and let's see if this runs now. There we go. So now that runs. Now that works. This is having the test. Very useful. Here. Okay. Now we only have those 2 children in there. This is great. This is absolutely great. Let's test this case. Okay. In this particular case, we've only got one frickin' child. The 3, 0. We've actually got these other ones as well. We don't want any of them. So how did we even get them, right? Like this. Oh no, that's actually okay, because these are the ones that never got expanded. So this one's okay. Let's try the other 4. 1, 2, 3, 4. And this sets them all to 1. This is great, because what this means is now if I fill out every single one of these, if we look at the root children, this one's full, this one's full, this one's full, and this one's full. Which means now, after doing all that work, now we can actually look at all of our grandchildren our children to determine if we need children at all. Right? So what I want to do in my set here. So we're doing our set. As soon as we set our current, sorry, where is it? As soon as we set our current here, we break, right? if we've managed to set it, as soon as we set the value, we need to actually at that point collapse our parents, as many of them as we need to. So in order to do that, I actually want to keep a track of all the nodes that we've gone through, because that's the tree that I might need to collapse. So let's take a look. Let's do this. Node tree equals array. Or actually, we're just going to put current in there. And then every time we choose a new current, we're going to pop that onto the node tree. And at the end of this function, let's console log our node tree. And I'm actually going to go inside, well, yeah, that's fine. And let's run this, and let's add here. Usually that console log just gets ignored. This really, I feel like this debugger is actually just broken. I think that might be the issue. I think, there we go. It was, thanks, Chrome. The debugger was just actually broken. All right, here is our node tree. And the first one was that 6, 6. Here's that one with 3, 3, the 2, 1, and then finally our actual node. So we can walk backwards up this tree node and determine if we can collapse parents. So what does that look like? Basically, that looks like if you have a parent like this, you look at all of your children and you look at all their values. If they have the same value, you do not need children, because you just set your value equal to that value, and then that represents that everything under you has that value. That's the whole point of a quad tree. Again, going back to this example here, if I know every single pixel under this square has all the same color, I don't need its children. I don't need to have children for it, because I know that they all have the same color. So in the same case here, I know if all these children have the same color, I don't need them because I can represent them with this single value here. So let's take a look at just how we would do that. All right. First of all, how would we check the children to see if their parent needs to be, is taken care of? So let's take a look. Function. Well, let's do it as a const collapse check collapse parent node. If the node has no children, then it's already collapsed. So we're just going to return. Okay. If it does have children, let's recurse into them. Actually, let's just do this. We're going to return node.children or node.value. We'll return its value. Okay. No, we'll just return true. That's totally fine. If we have no children, we're returning true. We're good to go. So what we want to do now is we want to find out, do any of our children have their own children? If any of our children have their own children, they may need to check if they need to collapse. So in this particular one, if I'm checking for this node, if it needs to collapse, if it can collapse, I need to check if this child can collapse first. And you say, listen, are you collapsible? Can you collapse into yourself? If so, then we probably are able to collapse it, and then we can check this one, see if it can be collapsed. It has to be that reverse recursion. We have to go down to the bottom and collapse everything there, and then we can go back up. So for each, for node.children as, no, that's not how you do this. I've been writing too much PHP. Const child of node.children. We're going to do the same thing. Result equals collapse parent child. Now, here's the great thing. If all these collapse parent functions return true, it means we are also collapsible. However, if result equals at any point false, it means we could not collapse that parent, which means we cannot collapse ourselves, which means we also must return false. That means if we get here, all children are collapsed. That's what that tells us. Because if at any point any of our children were not collapsed, we already returned false. So we say, okay, we got here. Our children all collapse. Excellent, very good. So what does that mean now? Now we got to check if they all have the same value. So first of all, I'm just going to set this to .children 0 .value. The reason is we're going to loop over all of our nodes, and if any of them have a value that's not the same as this value, that means that they don't all have the same value, which means that we cannot collapse. Okay. So we're going to say, okay, node children 0 equals value. Then we're going to loop over our children again of node.children. We could probably do this in one loop, but it's just a little bit less confusing if we do it this way. Sometimes writing more code is less complicated, if you can believe it. So if value does not equal child.value, not all values are the same, cannot collapse. Return false. Same thing. We get one of these. If any of these don't match, doesn't match, we return false, we're done. If we get here, all children have the same value and we can collapse. In that case, node.children becomes an empty array and node.value becomes value because that value is the first child's value, but all the children have the same value, so it doesn't matter which one we pick. And we return true. This will now take a node and collapse it, if necessary, collapsing all of its grandchildren and great-grandchildren as well. So what we can do now is we can use this on our node tree. Because the first thing we do is we push all of our elements into the node tree. We could just try to collapse the root and just say, look, just collapse the root, try it. If we've changed 1 pixel, that is extraordinarily wasteful because 90% of the branches on that tree haven't changed. They can't have changed. We changed 1 pixel, which means we only need to look at 1 sub-branch of that tree that could be collapsed. So we're going to start. Oops. Let's see again what that looks like. This node here is the node that we just set. We just changed this. This one is its parent, grandparent, and great-grandparent. We start from the end. We start from the bottom of that tree and work our way upwards and let those parents fan out as necessary to determine if they need to be collapsed. But we only really need to do that if we manage to collapse the previous level. If we didn't collapse the previous level, nothing has changed. Will change above it. Right? So if I'm looking at this tree here and this one collapsed, right? These children disappeared and got shrunk to here. That means this tree needs to check if it can do the same thing. If it cannot, there is no point checking this node because nothing changed. We don't need to check it. The fact that this is red is bothering me. We don't need to check this node if nothing changed. So we check the bottom one and they say, hey, did you collapse? Oh, you did collapse. Okay, well, cool. Let's move upwards. So what we're going to do is we have our node tree here. We're going to reverse that list and then loop through it. Because I want to go from the first one forward. Node tree, collapse parent. You notice this code's getting messy. We're still in the add function, and now it's like a 100-line function. This should be broken out as a helper function. Probably, actually, this create child code should be its own helper function. This code here as well, to figure out where we are and what index we're looking for, should also be its own helper function. That would clear things up. I'm not going to do it right now. I'm going to say node tree, dot reverse. That's just a JavaScript function. It reverses the order of the array. Now the first element is the bottommost. For once node of node tree, we're going to say, okay, here we are. Result equals collapse parent node. If we could not collapse this node, we're done. There's no point going on any further. If not result, break. That's pretty much it. If we could not collapse the parent, or that particular node, then we don't need to go any further because we will not be able to collapse the ones above it. Because they're just going to check and say, nah, something still has children. Can we collapse it? We can't. There's no point doing that work twice. If we could collapse it, then we let the loop continue and we go on to the next parent. So let's take a look and let's just see optimistically if that works. I run this here. Cool. We've got our value and value. What I'm expecting, I'm going to click this, and I'm expecting this 4, 0. I'm expecting that to collapse. And it did. Very cool. So this one, that one never collapsed. This particular one, same thing. If I change this value here, I expect that to collapse up. And it did. Now this one is going to be 4. I'm just going to do them all at once. And you notice as soon as I did that, they all collapsed up into this row here. Now I've got these 9 pixels here, all represented by this one value in my quad tree. And that is what a quad tree is good for. Because I can have these pixels and I can be like, yeah, here's this thing. Here's all these things in here. But they collapse themselves as appropriate. You can see that bar just jumped. If I change this, see it gets bigger, smaller, and way smaller now. Now I've only got 2 values that I'm storing for this, but I'm holding 18 different pixels. That's very cool. If I make this map a ton bigger, the amount of data that it needs to store starts shrinking as you get more contiguous blocks. I kind of wish I could actually show you the quad tree in here. That would be kind of cool and like show its boundaries. Unfortunately, table cells are not amazingly good for that. So the next thing we need to do is how do we remove an item? Like if I click this again, I'd really love if it would just turn back to blue. If it could go back to 0. That'd be pretty cool. Well, before we do that, let's actually clean up some of this code. All right. So what I want to do here is I want to take, first of all, this particular code of getting the child index, and I want to pull this into a helper because this code is basically identical, oops, to this. Wow, where the hell is it? I am completely lost in wherever the hell I am now. It's completely identical to the get. Here it is, all down here. This is completely identical to this code. Right here. It's the same code. It should be the same code. And the more that we change it, we want those changes to be propagated. So I'm going to copy all that code. I'm going to make a helper method here. I'm going to say function, okay, get child index for coordinates. It's going to pass in a node, an X, and a Y. I put this in here. We need to do something about this break. Current, well, let's just call this current then. And that should be okay. That'll handle all this stuff. And then we'll return child index. In this particular case, we're actually going to have to pull this out. So we're going to take this code and we're going to move it up to the top of our loop there. Because we don't, it could be there anyway, right? Like we don't need to know about halfway to do this check. This is a cheaper check that we can do without that. Then we're going to get rid of all this, and we're going to say child index equals get child index for coordinates current x, y. That's a lot cleaner because now I can also go all the way down here to my get method, and I can do the same thing. I can say child index equals get child index for coordinates current x, y. I'm actually going to take this, similar to what we did in the previous function, I'm just going to move it up to the top of that for loop. Totally fine. And we're going to get rid of all that code. Wow, look at how much simpler that is. Look at how clean that function is. If we get rid of all these console logs, that's so clean. This function actually can go up above here as well because it doesn't rely on the child index. It's only if we have to loop that we're relying on the child index. There we go. So that's our get function. Now, anytime I need to change any of that complicated code for how we get the child index, I change. You remember earlier in the stream, we ran into a bunch of problems with that. I change my child index here. Up here, same thing, except I've got this child creation. This is the same code. Let's test it. Let's run our test code. These should both be 1. and they're still both 1. So this is why it's nice to have some test code here, because I can make changes. And this, I want to go on a tangent a little bit. This is why you write unit tests in the first place. Is if I have a good suite of unit tests and I do a full refactor of my tree component like I just did, that was a pretty big code refactor. I took some really complicated code and moved it into another function. If there have been differences and changes, I want to know about that, right? I might break something. If I have a test case like this, I can verify that my system still works appropriately and I haven't broken anything. That's why it's valuable. Add children, okay? I actually want to pull this out into a whole other function as well, okay? So I'm going to make a function up here, and I'm going to call this function create necessary, children, current. Okay, the only thing it needs in here is current, because it's using the width, the height. It's using the width for all our checks. It doesn't need to return anything even. It just creates the necessary children. I can just pop that in here now. And I can get rid of this whole chunk of code. Okay, now this is an extremely simple loop. While true, if we got here, we found our pixel, set it and quit, get the child index for coordinates, and then create necessary children. Giving these functions appropriate names now, this code is much easier to understand. You can read this now. What I want to do now is I'm actually going to take this collapsed parent and I'm going to do the same thing to it. Take this out, put it in a function, and there we go. And just make it a regular function there. We get our node. There's nothing else that this is taking in. It's just working on that node and doing some work with it. And now down here, we can just call this. Collapse the tree as necessary to improve storage. Oops. Our add function is pretty simple now. Current node tree, we build our tree, we've got our while loop here, pretty small while loop. Then we've got just this little for loop down here that does this. All those functions were pulled out. Let me try this again, just make sure that works. Doesn't crash there. If I run this, and I'm going to do my same thing here and make sure that that all collapses. Very good. Very cool. The reason I wanted to do all that work just now is because when I implement remove, remove is almost going to be exactly the same as add. Okay? And I didn't want to duplicate 300 lines of code because I'm already just going to grab this, pretty much this entire thing here for add. Right? Because here's the fun thing about add. Remove doesn't actually exist. Technically. I mean, it kind of does, but we already have a collapsing function and everything defaults to 0. So if I'm actually doing a remove, I'm actually doing a set to 0. In fact, this is not technically add. This is set. So I'm just going to rename that. Rename it here. Rename it here. Oops. That. And then inside my app, I'm going to, oh God, where is it? Where's my onClick? There it is, set. Same thing. We're setting. And because the whole idea of remove is, oh, you delete that child and make sure that everything collapses okay. But we kind of already have code that does that, right? We already have code that says, oh, if my children are all the same, then I collapse them. The add or the set method already does that. And we actually don't want to delete children. That's not a thing that we want to do. We always want a node to have 4 children if any of them are distinct. So really, instead of deleting it, we'd just be setting it to 0. And we already have a method that does that. So let's do this. Let's say if value equals 1, let's just do this. Const new value equals value. If value equals 1, it's 0, otherwise it's 1. That might be a little confusing to you. This is basically a toggle. If the value is 1, we return 0. If the value is 0, it returns 1. It just flip-flops between them. So if I do that now, and I click this, the whole tree structure collapses. So this is the remove, right? I go through here, I turn all this stuff. It's like, oh yeah, we got that single value. I remove this one in the middle. It expands the children as necessary because that's what the add function already does. So now we have a basic structure that we can set this stuff in, and it will only store in a tree, it will only store the pixels that are not similar to their parent node. So if I do this and take that off, you notice how much that just dropped because that whole system just said, oh, this is all 0. Every 9 pixels in here is a 0. Now, if I wanted to have a destructible terrain, all I have to do is program a system that knows what coordinates to set for that destruction. I could get a square and I could say remove these 4 coordinates and just call that set method 4 times. And it would figure out how to do it. If we really wanted to optimize that a little bit more, we could actually go into our tree here and our set, we can make our set kind of pause on the collapse. And we could do a bulk operation. We could say, okay, we're going to be changing 100 elements here. Don't call collapse every time because we'll just call collapse at the end. Why? Because that's more efficient at that point. This is going to call the check collapse method every single time I set a single pixel. That's fine for what I'm doing right now. But if I'm setting in bulk, I want to make a bunch of changes and then collapse, right? And maybe I want to collapse the entire tree and figure out all that stuff. That's going to be more efficient if I just change 10,000 pixels, which I could do in this case. Maybe that's building the map. And you build the map and you generate 10,000 pixels. Then you tell it, okay, now go ahead and collapse and build those contiguous areas as necessary. And it'll go and build it, optimize that data, and then you can work with it. So I think at this point, we have completed what we wanted to do. We have built a quad tree. This is a specific tree now that as the values inside of it become more similar, it can collapse its children. And it also expands them in a quadrant fashion based on coordinates to figure out where it needs to be. Pretty cool. I think it's pretty cool. Does anyone have any questions on this? And like Yanko said earlier, this is the moment that we strive for, the moment when everything falls together and you realize it just works. Yeah, if you have questions, please type them in chat. I want you all to notice, though, when I first created this, I thought, oh, it's a binary tree. I want to be able to add and remove cells or nodes from it. As the structure went on, as we built it, we determined that add and remove were actually kind of the same thing because we built our remove in through this. We just really needed the ability to fetch it. Every single fetch and every single set on this tree is done in O log n because it is a tree. Trees by default work that way. And even if I look at my node tree or my collapsed parent here, this is also the way it's set up, kind of an O log n, because it only ever needs to go down log n nodes and then filter back up. So this is kind of a 2n log n, which becomes log n. So it's actually pretty efficient. As your map gets bigger and bigger and bigger, as long as you don't have that really terrible pattern that we discussed here. Because remember, if you do a pattern like this, let's actually do that. Now that we have this, let's set up our map that way. We'll just do some cross like that. Now we look at this whole map. There is none of these sections can be collapsed. All of them are fully extended, and none of them can collapse any further. And this is the longest this tree will ever get. Not too bad, because especially if you think about what's our depth here, 1, 2, 3, 4. The highest depth we have is 4. So at any point, to get any pixel set or get in this array, it takes 4 actions. That's pretty good. That's pretty damn good. Now, could we make that more efficient? Absolutely. If we had an array and we were storing all these pixels, we could absolutely get a specific position in that array in constant time because we can index the array based on X and Y coordinates. But that array will be memory heavy because it has to store one position for everything. This is the worst in memory this thing gets. As soon as I start removing these nodes, it'll start collapsing them. So if I pull in here, 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 you can see it's already getting smaller. There. As soon as I pull these in, like the whole thing gets much smaller. And so if you're not dealing with data that's exactly that nasty, oops, you can see it auto collapses it. This is an array that is space conscious, or not an array, a tree that is space conscious. It tries to collapse in on itself and make itself more space efficient. That can be really valuable because if you're running a modern game, you're running with probably 32 gigabytes of RAM, yes, but you're also running with a huge map. Imagine if you were trying to do every single pixel for a game like Far Cry. You do not want an array that big. However, a lot of those things are the same. A lot of them are very similar. And so this saves on space. Also, if you're trying to save a save game to the disk and someone's been able to change their terrain, right? You want to be able to have a compressed data format that indicates like it saves everything that they've done, but also doesn't save things it doesn't need to. So this is very efficient for that as well. Something, if anyone is interested enough, something that you could do that could be kind of cool is hook this up to the wavefront collapse algorithm that we built before. Do that wavefront collapse, but have this thing as that coordinate and see if you can get it to be more efficient because there's probably some contiguous blocks in there as well. The other cool thing about this particular tree is because we had set X and Y and get X and Y, it kind of behaves like a grid. This is not technically a tree. Like we don't use it like a tree. We use it like a grid. Under the hood, it acts and behaves like it's a tree structure. But because we were able to set and get any specific value at any point on that grid, this actually can behave like a two-dimensional array. Because what is a two-dimensional array but an X and Y? Let that blow your mind for a minute. Of course, to loop through this entire thing is still kind of expensive. As we saw before in our app here, if we loop through all our height and width, it's still actually like an n squared times log n. So this is definitely, if you have to loop through the entire map, it is definitely less efficient. Something you could do, however, is you could build a map renderer that understands how this tree structure works. We could have something that says, hey, get me a node, and actually have a renderer that does that same going through the tree. And because if it knows that there's just a rectangle to draw, drawing a single rectangle is a lot quicker than drawing each pixel in that rectangle. So rather than this get XY, we could also loop through the tree structure and set things appropriately like that. So that can be another thing to think about if you want to optimize on that. Yeah. But fun stuff. I'm glad we got to the end of this one. I was a little worried it wasn't going to happen. But yeah, I'll pause. I know I keep saying I'll pause for questions and I just keep talking. But I will actually, at this point, actually pause for questions. And maybe actually see if there's still even anyone in chat. Because OBS does not tell me that information. Oh, well, there's still 2 people watching. No worries if you don't have any questions. Don't feel any pressure at all. Please don't. I just want to make sure that it makes sense what I've done here and why I'm doing it this way. So yeah, fun stuff. This, I'll make sure when I put this up on YouTube, I'll include a link to the GitHub repository that this code is in, as I will be pushing all of this up. not the dist and the node modules, but all this actual code, so you can take a look at it. You can see the whole tree itself is 200 lines of code. Oh, the remove. Let's just get rid of that. Okay. Yeah, exactly 200 lines of code. Not too bad, right? That's not bad at all. JSON object. Yeah, this actually shouldn't be commented out. We can make it slightly more efficient. There's a couple ways like these. If I really was counting on trying to make the line length smaller, I'd make these all into one line and stuff like that. I'm not too worried about it. I'm also going to comment this out. Let's just run that test one more time. There we go. 1, 1. Beautiful. Good stuff. And so this is also a good example of how binary trees are constructed. You can see we have our tree node, we have our children. Technically, if you had a single child here, this becomes a linked list. So keep that in mind as well. If you want to do a linked list, much of the code is very similar, except you're not recursing into multiple children. You're usually just going to the next one via a current. And the algorithm for doing that is a lot simpler because it's not children, it's just next. But this is how you do a tree. If you want to do a binary tree that was like a sorted binary tree, you notice one of the big things about this is as we were recursing into our children, let me find this. We were actually using a specific algorithm to determine which child we went into. That means we are creating a sorted binary tree or an ordered binary tree as we go. I keep saying binary, an ordered quad tree as we go. And it's important for it to stay in order, otherwise things don't work. Yeah, I think if there's no questions from anyone, I'm going to call it there. I appreciate y'all showing up. I know this is kind of a weird hour, and I apologize for that. Next week is also going to be a little weird, and that's simply because I had other things scheduled before this stream started happening that were scheduled for those times. In a couple more weeks, we'll hopefully get back to the regular schedule. And we're hoping to have someone in May, probably actually a recruiter, come on and do an interview, do a little presentation on how their side of things work, right? And what tips and tricks you can use to just, appear better to recruiters, which is kind of important for a lot of you, I'd imagine. So yeah, thanks for coming, folks, and I'll see you all next time. Oh, I should have like an outro thing. It's just like stream has ended, but I'm not that on top of it. Yeah, it should be really exciting. I don't know exactly when in May that's going to be, but that's when we're kind of trying to line that up. Take care, folks. I'll see y'all later.